Hello, and welcome to Space Historians, where curiosity gets cozy and science takes the scenic route to slumber. Tonight, we're asking a question that sounds simple, but opens into something breathtaking. How big is our universe? It's the kind of question a child might ask, looking up at the stars with wonder still fresh in their eyes. And it's the kind of question that even scientists, with all their telescopes and mathematics, can only answer with a mix of precision and humility. Because the universe, it turns out, is not just big, it's big in a way that changes what the word big even means. Before we begin, I'd like you to take a moment to settle in. Let your breathing slow just a little. Let the weight of the day drift away like clouds moving across an evening sky. Tonight, we're not rushing anywhere. We're wandering gently through scales so vast they'll make your everyday worries feel beautifully small. I'm curious, where are you listening from tonight? What does your sky look like? Right now, is it dark where you are, with stars beginning to peek through? Or is it still daylight? The stars waiting patiently overhead, invisible but always there. It's funny to think that right now, as you rest, you're already inside the answer to our question. You're part of the universe, drifting through it on a small blue planet, orbiting a star that's just one among hundreds of billions. If you find comfort in these slow journeys through cosmic scale, if the vastness feels less like fear and more like peace, a like or subscribe helps others find this same gentle space. And to those who've already joined, thank you. You're part of this quiet exploration. Tonight's journey will take us from the familiar, the room you're in, the planet beneath you, to distances so enormous that light itself, the fastest thing in existence, takes billions of years to cross them. We'll measure the universe not in kilometers or miles, because those numbers collapse almost immediately, but in light, years, in time, in the patient crossing of ancient photons. So close your eyes if you'd like, or let them rest softly on something nearby. There's no need to picture everything perfectly. Just let the ideas wash over you like gentle waves. The universe is vast, yes, but you don't need to hold all of it in your mind at once. We'll take it piece by piece, scale by scale, until the immensity feels less overwhelming and more like a lullaby. We'll start close to home and drift outward, slowly, the way light itself travels, carrying us across distances that grow larger with each breath. And somewhere along the way, you might find that the bigness of the universe doesn't make you feel smaller. It makes you feel connected, part of something ancient and luminous, something that holds you gently even as it stretches beyond all imagining. Welcome to the question. Welcome to the vastness. Welcome to the slow, soft journey of discovering just how big our universe really is. 93 billion light years. That's the number. That's how wide the observable universe is, stretching in every direction from where you sit right now. 93 billion light years across, a distance so enormous that even saying it out loud doesn't help. The numbers are too large. They slide right past understanding and land somewhere in the space where words stop working. But here's what makes it even stranger. That number, vast as it sounds, only describes what we can see. The observable universe is just the part of the cosmos that light has had time to reach us from since the beginning. Beyond that horizon, space continues. Perhaps it goes on forever. Perhaps there are other regions, other galaxies, other stars shining in darkness we'll never glimpse. The universe we can measure might only be a tiny fraction of what truly exists. Let's start with something more familiar and work our way up. A light year is the distance light travels in 1 year, moving at about 300,000 kilometers per second. In 1 year, Light covers roughly 10 trillion kilometers. That's already hard to picture, but it's the basic unit we use when talking about cosmic distances because kilometers and miles give up almost immediately. They're too small for the task. Our solar system, the Sun and all its planets, stretches about 6 billion kilometers across, if you count to the edge of Neptune's orbit. If you include the Oort cloud, that distant shell of icy debris, it might extend a light year or more. But even that immense bubble is local. The nearest star beyond our Sun, Proxima Centauri, is over 4 light years away. That's the gap to our closest neighbour. And already we're measuring in years of light's travel. The Milky Way galaxy, our home, is about 100,000 light years from edge to edge. If you were a beam of light leaving one side, it would take you 100,000 years to reach the other. Civilizations could rise and fall in that time. Species could evolve. Mountains could form and erode. And you'd still be crossing, moving at the fastest speed possible, and still nowhere near done. But the Milky Way is just one galaxy. There are hundreds of billions of others scattered throughout space, each one a vast system in its own right. Some are larger than ours, some smaller, but all of them separated by distances that make the Milky Way's width seem almost modest. Andromeda, our nearest large galactic neighbour, is about 2.5 million light-years away. The light we see from it tonight left that galaxy before humans existed, before our ancestors walked upright, before stone tools were shaped. And that's still local. The observable universe stretches far beyond Andromeda, beyond our local group of galaxies, beyond clusters and superclusters, all the way out to a boundary defined not by walls or edges, but by time. Light from the most distant galaxies has been travelling for over 13 billion years to reach us. Those galaxies are so far away that we're seeing them as they were when the universe itself was young, less than 1 billion years old. Here's where the number 93 billion light-years comes from. You might think that if light has been travelling for 13 billion years, the edge of the observable universe should be 13 billion light-years away. But space itself has been expanding during all that time. The galaxies we see in the distant past have moved even farther from us as space stretched. By now, those same galaxies are about 46 billion light-years away in one direction and the same distance in the other, giving us that total width of 93 billion light-years. It's a number that breaks the mind because it's not just large, it's large in a way that makes every other scale we know feel insignificant. If you tried to drive across the observable universe at highway speed, it would take longer than the age of the universe itself, trillions upon trillions of years, and you still wouldn't finish. If you counted 1 light-year per second, it would take nearly 3,000 years just to count to 93 billion, and even then, you'd only be counting the distance, not the stars, not the galaxies, not the space between them. But the universe doesn't care about our ability to picture it. It exists at this scale regardless of whether we can grasp it. And perhaps that's the hook, the thing that pulls you in. The universe is so big that understanding it requires letting go of the need to picture it all at once. You can't hold it in your mind like you hold a map. You can only visit it piece by piece, scale by scale, moving outward from the familiar until you reach the edges of what light and time allow. That vastness is what we're exploring tonight. Not just the number, though the number is astonishing, but what it means, what it feels like to live in a universe this large, what it tells us about time, space, and our place within it all. Because even though 93 billion light-years is incomprehensibly vast, we're still here, inside it, part of it, able to think about it and wonder. Every star you've ever seen with your own eyes belongs to our galaxy, the Milky Way. every constellation, every twinkling point of light, all of them are part of this one small corner of one galaxy among billions. The farthest star you can see without a telescope is only a few thousand light years away, barely a fraction of the Milky Way's width, let alone the universe beyond. And yet that distant star, that faint glimmer, is still sending its light across space, across time, to reach your eyes tonight. The universe doesn't announce its size with fanfare. It reveals itself slowly, gently, through the patient work of observation. Astronomers measure the light from distant galaxies, calculate how long it's been travelling, and piece together the larger picture. Each new telescope, each new technique, extends our view a little farther. The Hubble Space Telescope showed us galaxies billions of light years away. The James Webb Space Telescope is now looking even deeper, revealing structures from the universe's earliest days. And still, with all our tools and all our measurements, we can only see so far. The observable universe has a horizon, a limit set by the speed of light and the age of the cosmos. Beyond that horizon, light hasn't had time to reach us yet. It may never reach us, because space is expanding, carrying distant regions away faster than light can cross the growing gap. The universe we can see is only a bubble, a sphere of visibility centered on us. And beyond it lies more, possibly infinitely more, forever out of reach. That's the hook. That's the impossible, beautiful, overwhelming truth that opens this journey. The universe is 93 billion light years wide, at least the part we can see. And that part, vast as it is, might only be the beginning. The real universe, the totality of everything that exists, could be larger still. It could be infinite. It could stretch on forever, with no edge, no end, no final number to count toward. And you're inside it, right now, resting on a small planet in one galaxy among trillions, part of a cosmos so large that even light, the fastest traveller in existence, takes billions of years to cross it. That's where we're starting. That's the question we're gently exploring. How big is the universe? And what does it mean to live inside something so impossibly vast? Let's find out together, one light year at a time. Let's begin somewhere familiar, not with distant galaxies or cosmic horizons, but with you, right here, right now. You're resting in a room, or perhaps outside under the open sky. Around you, the walls or the trees or the darkness define a space you can understand. A few meters in one direction, a few more in another. This is a scale that fits comfortably in the mind. You can walk across it, measure it, touch its boundaries. Now imagine stepping outside your immediate space and thinking about the town or city you're in. Maybe it stretches for a few kilometers, maybe dozens. You can drive across it in minutes or hours. You know its streets, its landmarks, the way it fits into the landscape around it. This is still a human scale, a size that matches the way we move through the world. Zoom out further and you're looking at a country, then a continent. Earth itself becomes visible, a blue sphere suspended in the black. Its diameter just under 13,000 kilometers. From this height, cities vanish into dots. Mountains flatten into textures. The planet, which feels so large when you're standing on it, becomes small enough to hold in a single view. And this is where the shift begins, where familiar scales start giving way to something larger. Earth orbits the Sun at a distance of about 150 million kilometers. Astronomers call this distance an astronomical unit, a convenient measure for thinking about the solar system. It takes light from the Sun about 8 minutes to travel that gap, which means when you see the Sun in the sky, You're seeing it as it was 8 minutes ago. Already, even this close to home, distance becomes a measure of time. The moon, our nearest neighbour, is only about a light second away. Radio signals take just over a second to travel between Earth and the moon. When astronauts landed there in 1969, their voices travelled back to mission control at the speed of light, delayed by that single second. It feels instant, but it's a reminder that even nearby space introduces gaps that light must cross. Beyond the moon lies the rest of the solar system. A collection of planets, moons, asteroids, and comets, all bound to the sun by gravity. Mercury orbits closest, just under 60 million kilometers from the sun. Venus comes next, then Earth, then Mars. These inner planets occupy what we might call the warm zone, close enough to the sun that sunlight is strong. Temperatures vary, but remain within a range where rock and metal can exist in familiar forms. Farther out, the gas giants dominate. Jupiter, the largest planet, orbits at about 780 million kilometers from the sun. Saturn, with its rings, lies twice as far. Uranus and Neptune drift even more distantly, cold and blue, their atmospheres thick with methane and ice. Neptune, the farthest planet, orbits at about 4.5 billion kilometers from the sun, taking light over 4 hours to reach it. If you stood on Neptune and looked back, the sun would appear as a bright star, no longer a blazing disk but a distant point of light. But even Neptune isn't the edge of the solar system. Beyond it lies the Kuiper Belt, a region of icy bodies stretching billions of kilometers farther. Pluto, once called the 9th planet, is part of this belt, along with countless other frozen remnants from the solar system's formation. And beyond the Kuiper Belt, even more distant, lies the Oort cloud, a vast spherical shell of comets surrounding the sun at a distance that might reach halfway to the nearest star. This cloud, if it exists as theory suggests, marks the true boundary of the sun's influence, extending perhaps a light year or more into space. This is the setting we start from, a solar system stretching light hours, possibly a light year across. A neighborhood around one star, filled with planets and debris, all orbiting together through the galaxy. It's vast by human standards, but compared to what lies beyond, it's tiny. The solar system is a grain of sand on a beach that stretches farther than we can see. But it's also home. Every human being who has ever lived was born within this system. Every star you can see with your naked eye. With a few exceptions, like distant galaxies barely visible under dark skies, belongs to our galaxy, the Milky Way. The solar system is our address, the place we occupy in a much larger structure, and understanding its scale helps us take the first step outward, because from here, the distances only grow. The sun itself is not unique. It's one star among hundreds of billions in the Milky Way, a medium-sized yellow dwarf burning steadily, about 4.5 billion years old, with perhaps another 5 billion years of life left before it swells into a red giant and eventually fades. Around it, 8 planets orbit, along with at least 5 recognized dwarf planets and countless smaller bodies. Moons orbit planets. Asteroids drift in belts. Comets swing in from the outer reaches, their tails glowing as they pass near the sun's warmth. This system formed about 4.5 billion years ago from a collapsing cloud of gas and dust. Gravity pulled material together, the center igniting into the sun, the rest flattening into a disk where planets coalesced from smaller pieces over millions of years. The process wasn't smooth. Collisions were common, worlds smashing together, some merging, others shattering. The solar system we see today is the survivor of that violent beginning, a relatively stable configuration that has lasted billions of years. And yet, even this stability is temporary. The planets don't orbit in perfect circles. Their paths are slightly elliptical, tilted, influenced by each other's gravity. Over millions of years, these influences accumulate, shifting orbits slightly, introducing small changes that might one day, in the far future, lead to larger disruptions. But for now, the solar system is balanced, a family of worlds held together by the sun's gravity, moving in rhythms that have persisted since before life appeared on Earth. From any planet in this system, the view outward is limited. If you stood on Mars and looked up, you'd see stars scattered across the sky much like they appear from Earth. The constellations would be familiar, only slightly shifted by the different vantage point. If you travelled to Jupiter, the sky would still look similar, though the sun would appear smaller, less fierce. Even from Neptune, the farthest planet, the stars would remain in their familiar patterns, because the distances within the solar system, vast as they are tiny compared to the distances between stars. This is the setting, the stage where our story begins. A solar system orbiting through a galaxy, one small bubble of light and gravity in a much larger sea. When we talk about the size of the universe, we're starting here, from this familiar neighborhood, and then moving outward, step by step, scale by scale, watching as each layer reveals something vaster than the one before. The room you're in, the planet beneath you, the solar system surrounding you, these are the opening frames of a journey that will take us across distances, measured not in kilometers but in light years, not in minutes but in billions of years. And even though those distances will grow incomprehensibly large, we'll always be able to trace our way back here, to this small blue planet orbiting an ordinary star, because this is where the journey starts. This is where you are. And from here, the universe stretches outward in every direction, waiting to be explored, not physically, not in a lifetime or a million lifetimes, but in thought, in imagination, in the slow, patient work of understanding. The setting is familiar, comfortable, knowable, and that makes the vastness beyond it all the more striking, because every step outward reveals that what felt large, the solar system, the distances between planets, is only the beginning. So as you rest here, in this room, on this planet, in this solar system, let yourself feel the comfort of scale. You're somewhere you can understand, somewhere you belong. And from this safe, familiar place, we'll begin drifting outward, gently, until the numbers grow so large, they stop feeling like numbers and start feeling like something else entirely. Something vast, something beautiful, something that holds you even as it stretches beyond all comprehension. This is the setting. This is home. And from here, the universe begins. For most of human history, we thought the universe was small, not small in the way we describe it today, but small enough that the mind could hold it. The Earth was the center, surrounded by the moon, the sun, the planets, and the stars, all arranged in crystalline spheres, rotating overhead. The farthest star was thought to be perhaps a few million kilometers away, distant but not inconceivably so. The universe had edges, boundaries, a size that fit within the framework of what people could imagine. Then, slowly, over centuries, that framework began to crack. The first break came when we realized Earth wasn't the center. Copernicus, in the 1500s, suggested that Earth orbits the Sun, not the other way around. It was a radical idea, one that challenged everything people believed about their place in the cosmos. But observations confirmed it. The planets moved in ways that only made sense if the sun was at the center, not Earth. The universe suddenly felt larger because we were no longer its focus. Galileo, peering through his telescope in 1610, saw moons orbiting Jupiter. If moons could orbit another planet, then Earth wasn't unique. The universe wasn't built around us. It was a system of many worlds, and we were just one among them. He also saw that the Milky Way, that faint band across the night sky, was made of countless stars, too faint to see individually. The implications were staggering. If the Milky Way contained so many stars, how large must it be? But even then, the universe was thought to be only the Milky Way. Everything we could see, all the stars, all the faint nebulae, they were assumed to be part of one system, our galaxy. The Milky Way was the universe, and the universe was the Milky Way. The two were the same. The idea that other galaxies existed, entire systems of stars beyond our own, hadn't occurred to anyone yet. There was no evidence for it, no reason to suspect it. That changed in the 1920s. Edwin Hubble, using the largest telescope in the world at the time, the 100-inch Hooker telescope at Mount Wilson Observatory, turned his attention to a faint smudge of light in the constellation Andromeda. For years, astronomers had debated what these nebulae were. Some thought they were clouds of gas within the Milky Way, regions where stars were forming. Others suspected they might be something more distant, but no one could prove it. Hubble found the proof. He identified individual stars within the Andromeda Nebula, specifically Cepheid variable stars, which pulse in brightness at regular intervals. The period of their pulsation is directly related to their true luminosity. By measuring how bright they appeared compared to how bright they should be, Hubble calculated their distance. Andromeda was nearly 1 million light-years away, far beyond the boundaries of the Milky Way. It wasn't a nebula, it was another galaxy. Overnight, the universe expanded. What had been thought to be the entirety of existence, the Milky Way, was suddenly just one galaxy among many. The implications rippled through astronomy and beyond. If Andromeda was a separate galaxy, then the other nebulae scattered across the sky were likely galaxies too. The universe wasn't a single system. It was a cosmos filled with countless galaxies, each one a vast collection of stars, separated by enormous distances. Hubble didn't stop there. He continued measuring distances to other galaxies, using Cepheid variables and other techniques. What he found was even more surprising. The galaxies weren't just scattered through space, they were all moving away from us. The farther a galaxy was, the faster it seemed to be receding. The light from distant galaxies was shifted toward the red end of the spectrum, stretched by motion, a phenomenon called redshift. This discovery led to one of the most profound realizations in science. The universe wasn't static, it was expanding. Space itself was growing, carrying galaxies apart like dots on an inflating balloon. If the universe was expanding now, that meant it must have been smaller in the past. Trace the expansion backward, and you arrive at a moment when everything was compressed into an incredibly small, hot, dense state. This was the beginning, the origin of everything. Scientists called it the Big Bang. The discovery that the universe is expanding changed everything. It meant the universe had a history, an age, a beginning. It meant the cosmos was dynamic, not eternal and unchanging. And it meant the universe was far larger than anyone had imagined. If galaxies billions of light years away were moving apart, then space stretched across distances that made the Milky Way seem tiny by comparison. Astronomers began measuring the rate of expansion, trying to understand how fast the universe was growing. They discovered that the expansion wasn't just happening, it was accelerating. Some unknown force, later called dark energy, was pushing galaxies apart faster and faster. This acceleration meant the universe's future would be different than expected. Instead of eventually slowing down and perhaps collapsing, it would continue expanding forever. Galaxies drifting farther and farther apart until, in the distant future, most would vanish beyond the horizon of visibility. The realization that space was bigger than we thought wasn't just about distance. It was about time, about origins, about the nature of reality itself. Before Hubble, the universe could have been eternal, unchanging, a static backdrop. After Hubble, it became clear that the universe had a beginning, that it was still growing, and that its size was tied to its age. The farther you look in space, the farther back in time you see, because light takes time to travel. The most distant galaxies we observe are seen as they were billions of years ago, when the universe was young. Because the universe is only about 13.8 billion years old, light has only had that much time to travel. There's a horizon beyond which we cannot see, not because there's nothing there, but because the light from those regions hasn't reached us yet. The universe might extend far beyond what we can observe, possibly infinitely, but we're confined to seeing only the portion that light has had time to reveal. The discovery of the universe's true size was gradual, built on centuries of observation and thought. Each generation pushed the boundaries a little farther. First, we learned that Earth wasn't the center. Then, that the solar system was just one of many around one star. Then, that the Milky Way was one galaxy among billions. And finally, that even those billions of galaxies were only the visible part of a cosmos that might stretch endlessly beyond. Each step outward was humbling. Each realization made us smaller in comparison to the whole. But each step also expanded what we could know, what we could understand. The universe revealed itself slowly, patiently, through the work of people who looked up and refused to accept that the sky's mysteries were unknowable. They measured, calculated, observed, and pieced together a picture of a cosmos far grander than anyone had dreamed. And so the discovery wasn't a single moment, but a process, a slow awakening to the scale of existence. The universe was bigger than we thought. It was still growing. It had a beginning and would have a future. And we, tiny as we were, could measure it, map it, and begin to understand it. That discovery, that expansion of perspective, is one of the great achievements of human thought. It took us from a small, enclosed cosmos to an infinite, expanding one, and it set the stage for everything we now know about the size, age, and nature of the universe. When you look up tonight and see the stars, you're seeing the result of that discovery. Those points of light are not painted on a nearby dome. They're suns, some closer, some farther, scattered across distances that light takes years to cross. And beyond them, too faint to see, lie galaxies, billions of them, each one a city of stars, all moving apart in the grand expansion that began nearly 14 billion years ago. The discovery of the universe's size didn't make the stars less beautiful. It made them more so, because now we know what they are, how far they've travelled, and how much time their light has spent crossing the dark to reach us. That knowledge doesn't diminish wonder, it deepens it. When the true size of the universe became clear, when astronomers realized that galaxies stretched billions of light years in every direction, the immediate response was not excitement, but something quieter, something more personal. It was the feeling of becoming small. Not small in a diminishing way, but small in a way that shifted perspective, that made everyday concerns feel lighter, that reminded people of their place in something far larger than themselves. Before the discovery, humans could imagine being important, central, significant. Earth was the stage, and the universe was built around it. Even after Copernicus moved Earth from the center, the Milky Way could still be thought of as the universe, and we could still feel like inhabitants of the whole. But once Hubble showed that the Milky Way was just one galaxy among billions, that sense of centrality vanished. We weren't at the center. We weren't even close. We were on a small planet, orbiting an average star, in one spiral arm of one galaxy, among countless others. That realization hit different people in different ways. Some found it unsettling, even frightening. If the universe was so vast, what did that say about human life? If we occupied such a tiny corner of space, how could anything we did matter? The scale felt overwhelming, almost crushing. It was like standing at the edge of an ocean and realizing that the water stretches farther than you can see, that you're just one grain of sand on a beach that extends forever. But others found comfort in the smallness. If the universe was so large, then individual worries, anxieties, the petty troubles of daily life suddenly seemed less heavy. The universe didn't care about missed appointments or difficult conversations or the things that felt important in the moment. It continued, vast and indifferent, and that indifference was strangely freeing. You could let go, knowing that in the grand scale of things, most problems were temporary, small, manageable. The philosopher Blaise Pascal, writing centuries before the full scale of the universe was known, captured this feeling when he said that the eternal silence of infinite spaces terrified him. He was responding to the idea that space might be larger than the human mind could hold, that we might be adrift in something incomprehensibly vast. But terror isn't the only response. For many, the silence isn't terrifying. It's peaceful. It's a reminder that the universe doesn't demand anything from us. It simply exists, and we exist within it, for a brief time, part of its unfolding. The feeling of becoming small also brought humility. Humanity has often placed itself at the center of things, assuming that we're special, unique, the purpose for which everything else was created. But the universe's size suggests otherwise. There's no evidence that it was made for us. It's simply too large, too old, too filled with other stars and galaxies for Earth to be its focus. We're here, yes, but we're here as one outcome among countless possibilities, one planet among trillions, one species among perhaps many others scattered across the cosmos. That humility can be healthy. It tempers arrogance, reminds us that we're part of something larger, that our actions, while important to us, don't reshape the universe. The stars will burn whether we exist or not. Galaxies will drift apart. Space will expand. We're passengers, observers, participants in a process that began long before us and will continue long after. But humility doesn't mean insignificance, and this is where the response to the universe's size becomes more nuanced. Yes, we're small compared to the cosmos, but we're also capable of understanding it, measuring it, describing it. No other species, as far as we know, has looked up and asked how big the universe is. No other creature has built telescopes, calculated distances, traced light across billions of years. That ability, that curiosity, is rare, perhaps even unique, and it gives our smallness a different quality. Carl Sagan, one of the great communicators of astronomy, captured this balance beautifully when he described Earth as a pale blue dot, a tiny speck in a photograph taken by the Voyager spacecraft from the edge of the solar system. In that image, Earth is barely visible, a single pixel of light suspended in a sunbeam. Sagan used the image to remind people of our smallness, but also of our preciousness. This tiny dot, he said, is home. It's where everyone we've ever known has lived, where every human story has unfolded. Its smallness doesn't make it unimportant. It makes it irreplaceable. The feeling of becoming small, then, is not about losing importance. It's about gaining perspective. It's about realizing that the universe doesn't revolve around us, but that we're still part of it. We're made of the same atoms that make stars. The carbon in our bodies, the oxygen we breathe, the calcium in our bones, all of it was forged in stellar furnaces billions of years ago and scattered into space when those stars died. We're not separate from the universe. We're part of its fabric, woven into its history. That connection is where the response shifts from feeling small to feeling connected. The universe is vast, yes, but it's also intimate. Every atom in you has travelled across billions of years to be here now. You're not an outsider looking at the cosmos from a distance. You're inside it, made of it, participating in it. The bigness doesn't exclude you, it includes you. There's also a strange comfort in knowing that the universe is so much larger than our problems. When something difficult happens, when life feels overwhelming, it can help to remember that beyond all of it, the stars are still burning, galaxies are still turning, space is still expanding. The universe continues, patient and steady, and you're part of that continuity. Your troubles are real, but they're also temporary, small against the backdrop of cosmic time. This doesn't mean problems don't matter. They do. They matter deeply to the people experiencing them. But perspective helps. It softens the edges, makes the hard things feel a little more bearable. Knowing that you're part of something vast and ancient can be grounding, a reminder that you're held, in a sense, by the same forces that hold galaxies together. The feeling of becoming small is not the end of the response. It's the beginning. It's the first moment of realization, the shift in perspective that opens into something deeper. Once you've felt the smallness, once you've accepted it, you can begin to explore what it means. You can ask what it means to be small but aware, finite but capable of imagining infinity, brief but able to understand billions of years. And that exploration leads to wonder, not the overwhelming, crushing kind of wonder, but the gentle kind, the kind that makes you look up at the night sky and feel grateful just to be here, just to see it. The universe is vast, you are small, and somehow both of those things are okay, more than okay. They're part of the same story, the same quiet unfolding that includes everything from galaxies to thoughts, from light years to heartbeats. So when you feel small tonight, when the size of the universe presses in, let it. Let yourself feel the scale, and then let it soften. Let it become something gentler, something that holds you instead of overwhelming you. Because the universe, vast as it is also where you are. And being here, being part of it, even for a brief moment, is enough. 93 billion light years, 400 billion stars in the Milky Way, 2 trillion galaxies in the observable universe. These numbers are facts, measurements, the result of careful observation and calculation. But when you hear them, they don't quite land, do they? They slide past understanding and settle somewhere in the space where words stop working. Because these aren't numbers in the way we usually use them. They're too large. They've crossed some invisible threshold where quantity becomes quality, where counting becomes something else entirely. Think about smaller numbers for a moment. You can picture 10 of something easily. 10 apples, 10 people, 10 stars in the sky. 100 is harder but still manageable. You might struggle to visualize 100 objects all at once, but you can imagine rows of 10 10 times over, and arrive at the total. 1,000 is where things start to blur. Picturing 1,000 individual things is difficult. You have to use metaphors, comparisons, groupings, but it's still conceivable. 1,000,000 though, that's where the mind starts to stumble. 1,000,000 is 1,000 thousands. If you counted one number per second without stopping, it would take you 11.5 days to reach 1,000,000. That's already longer than most of us can stay awake, longer than we'd ever want to count. And yet, 1,000,000 is nothing compared to the numbers we use to describe the universe. 1,000,000,000 is 1,000 millions. If you counted one per second, it would take you over 31 years. Not days, years. Most of a human lifetime spent just counting, and you'd only reach 1,000,000,000. 1,000,000,000,000, 1,000 billions, would take over 31,000 years. That's longer than recorded human history, longer than agriculture, longer than cities, longer than written language, and we're using trillions to describe galaxies, stars, distances. At some point, these numbers stop being numbers in the traditional sense. They become symbols pointing at vastness, markers that say more than we can count, more than we can picture, more than our minds were built to hold. When someone tells you the observable universe is 93 billion light years across, the number itself doesn't convey the reality. It's a placeholder, a way of saying this is so large that language fails. And this is the contradiction at the heart of cosmic scale. We can measure the universe with extraordinary precision. We know distances to the nearest galaxy, the farthest quasar, the edge of the observable horizon. We can calculate how many stars exist, how many planets orbit them, how much matter fills space. Our measurements are accurate, repeatable, verified by multiple methods. The numbers are real, but the experience of those numbers, the ability to feel what they mean, escapes us. It's like looking at a photograph of a mountain. You can see its shape, its size relative to the trees at its base, the way it rises into clouds, but the photograph doesn't convey what it's like to stand at the bottom and look up, to feel the scale pressing down, to sense the weight of stone and ice towering above you. Numbers are like that photograph. They show the shape of the universe, but they don't carry the feeling of it, so we use comparisons. If every star in the Milky Way were a grain of sand, you'd need several large trucks to carry them all. If the sun were the size of a basketball, Earth would be a tiny bead a few meters away, and the nearest star would be another basketball thousands of kilometers distant. These comparisons help, a little. They give the mind something to grasp, a familiar scale stretched to fit an unfamiliar one. But they're still metaphors, still translations, still approximations of something that resists approximation. The contradiction deepens when you realize that we've only had these numbers for about a century. Before the 1920s, we thought the Milky Way was the entire universe. The distances we now casually describe in billions of light years were completely unknown. In less than 100 years, the known size of the universe expanded by factors of billions, and in that same time, we went from not knowing other galaxies existed to counting trillions of them. The expansion of knowledge happened faster than the expansion of the universe itself. But even with that knowledge, even with all our telescopes and calculations, we can't make the numbers feel real in the way that smaller numbers do. You can understand that you have 2 hands, 10 fingers, 100 hairs on your arm. Those numbers are experiential, tied to your body, to things you can see and touch. But 2 trillion galaxies? That's abstract. It's a concept, not an experience. And no matter how many times you hear it, it stays abstract. This contradiction is not a failure. It's not something to overcome. It's simply a feature of scale. Our minds evolved to deal with numbers in the tens, hundreds, maybe thousands. That's the range of human social groups, the number of objects we might need to track, the scale of distances we could travel in a lifetime. Evolution didn't prepare us for billions. It had no reason to. Nothing in the ancestral environment required thinking at that scale. So when we encounter numbers that large, we do the best we can. We measure them, write them down, use them in equations. But we don't feel them the way we feel 10 or 100. And perhaps that's okay. Perhaps the contradiction is part of the beauty. The universe is so large that it exceeds our grasp, yet we can still describe it. We're small enough to fit on one planet, but capable enough to measure billions of light years. That gap between what we can calculate and what we can feel is where wonder lives. It's the space between knowledge and experience, between facts and feelings, between the number and the vastness it points toward. There's a quiet humility in accepting this. We can know without fully comprehending. We can measure without fully picturing. We can describe the universe in numbers that stop feeling like numbers, and that's enough. The numbers are true even if they don't land in the body, even if they slide past intuition. They're the best tools we have for capturing something uncapturable, for pointing at a reality too large to hold. Sometimes, when you hear these numbers, it helps to just let them wash over you without trying to grip them. 93 billion light years, 2 trillion galaxies, 400 billion stars. Don't try to picture each one. Don't try to count them or imagine them all at once. Just let the numbers be what they are. Signposts pointing at immensity. Reminders that the universe is larger than thought, vaster than imagination, wider than anything your mind was built to contain. The contradiction is that we're finite beings trying to describe the infinite, or at least the nearly infinite. We're small, temporary, limited in what we can directly experience. But we're also curious, clever, persistent. We've built tools that extend our senses, mathematics that extends our reasoning, and language that extends our ability to share what we've learned. And through those extensions, we've managed to map a universe so large that the map itself barely fits in the mind. So, when the numbers stop feeling like numbers, when they blur into something abstract and untouchable, that's not a sign that the universe is unknowable. It's a sign that the universe is exactly what the numbers say it is. Vast beyond intuition, large beyond feeling, real beyond comprehension. And we, small as we are, have managed to measure it anyway. That's the contradiction. That's the beautiful, impossible truth. The universe is too big for us to fully grasp. Yet we've grasped enough to know how big it is. We can't picture 93 billion light years, but we can say it, measure it, confirm it. We can't imagine 2 trillion galaxies, but we can count them, map them, study them. The numbers stop feeling like numbers, and yet they're still numbers, still true, still pointing at something real. And maybe that's all we need. Not full comprehension, but awareness. Not complete understanding, but direction. The numbers tell us which way to look, how far to reach, what scale we're dealing with. And even if we can't hold that scale in our minds the way we hold smaller things, we can still acknowledge it, honor it, rest in the knowledge that the universe is larger than we'll ever fully feel. So let the numbers be strange. Let them stop making sense in the usual way. Let them become something other than counting, something more like poetry, something that points without fully explaining. The universe is 93 billion light years wide, and that number, impossible as it feels, is as close to the truth as we can get. And sometimes being close is enough. Measuring the universe is not like measuring a room. You can't stretch a tape measure across space, can't walk from one end to the other counting your steps. The universe is too large, too distant, too filled with complications. Light bends around massive objects. Space itself expands, stretching the distances between galaxies. Time and distance are woven together in ways that make simple measurements impossible. So astronomers had to develop theories, models, and methods that could capture something uncapturable, that could give us numbers where direct observation failed. The first theory that mattered was the idea that light travels at a constant speed. This seems simple now, but it was revolutionary when it was confirmed. Light, no matter where it comes from or how fast the source is moving, always travels at the same speed through empty space, roughly 300,000 kilometers per second. This constancy makes light a reliable messenger, a way to measure distance by measuring time. If you know how fast light moves and how long it's been traveling, you can calculate how far it's come. This led to the concept of the light year, a unit of distance based on time. 1 light year is the distance light travels in 1 year, about 10 trillion kilometers. It's not a measure of time, though the name suggests it. It's a measure of distance, one that scales naturally to cosmic proportions. When astronomers say a galaxy is 2 million light years away, they mean the light we see tonight left that galaxy 2 million years ago. Distance and time collapse into one measure, because at cosmic scales you can't separate them. But how do you measure the distance to something too far to reach, too faint to see clearly? That's where the theories come in. One of the earliest methods was parallax, the same trick your brain uses to judge depth. Hold your finger in front of your face and look at it with one eye, then the other. Your finger seems to shift position relative to the background. That shift, caused by viewing from two different positions, can be used to calculate distance. For stars, astronomers use Earth's orbit as the baseline, observing a star from opposite sides of the Sun 6 months apart. The tiny shift in the star's position reveals how far away it is. Parallax works beautifully for nearby stars, but it has limits. Beyond a few thousand light years, the shift becomes too small to measure accurately. For more distant objects, astronomers needed a different approach. They found it in standard candles, objects whose true brightness is known. If you know how bright something should be, and you can measure how bright it appears, you can calculate its distance. The farther away it is, the dimmer it looks. Cepheid variable stars became the first widely used standard candles. These stars pulse in brightness with regular periods, and the period of pulsation is directly related to their true luminosity. A Cepheid with a longer period is intrinsically brighter than one with a shorter period. By measuring the period, you know the star's true brightness. By measuring its apparent brightness, you calculate its distance. Edwin Hubble used Cepheids to measure the distance to Andromeda, proving it was another galaxy far beyond the Milky Way. For even greater distances, astronomers use supernovae, specifically Type Ia supernovae, which occur when a white dwarf star reaches a critical mass and explodes. Because the mass at which this happens is always the same, the explosions have the same intrinsic brightness. They're incredibly luminous, outshining entire galaxies for a brief time, which makes them visible across billions of light years. By measuring their apparent brightness, astronomers can calculate distances to galaxies far beyond the reach of Cepheids. Another theory that revolutionized cosmic measurement was the discovery of redshift. When galaxies move away from us, their light is stretched, its wavelength elongated toward the red end of the spectrum. The faster a galaxy recedes, the greater the redshift. By measuring this shift, astronomers can determine both the speed at which a galaxy is moving away and, using Hubble's law, its approximate distance. This method works for galaxies billions of light years away, far beyond the reach of standard candles. Hubble's law itself is a theory, a relationship between distance and recession speed. It says that the farther away a galaxy is, the faster it's moving away from us. This isn't because galaxies are flying through space, but because space itself is expanding. The relationship between distance and speed is linear, at least on large scales, which means you can use one to calculate the other. Measure the redshift, apply Hubble's law, and you get the distance. But all of these methods depend on assumptions, on models of how the universe works. Cepheids assume we understand stellar physics correctly. Supernovae assume they all explode the same way. Redshift assumes the expansion of space is uniform. These assumptions are tested, refined, and verified. But they're still assumptions. That's why astronomers use multiple methods whenever possible, checking one against another, looking for consistency. When different approaches give the same answer, confidence grows. There's also the cosmic distance ladder, a series of methods that build on each other. Parallax measures nearby stars. Cepheids extend the range to nearby galaxies. Supernovae reach even farther. Redshift goes farthest of all. Each rung of the ladder is calibrated using the one below it, and errors can propagate upward. If the first rung is slightly off, all the higher ones shift. That's why measuring cosmic distances is tricky, why the numbers sometimes change as methods improve, why there's ongoing debate about the exact value of Hubble's constant, the rate of the universe's expansion. But despite these uncertainties, the theories work. They give us numbers that are consistent, that match observations, that predict what telescopes will find when they look farther. The universe is 93 billion light years across, not because someone measured it directly, but because the theories, tested and refined over decades, converge on that number. It's the best answer we have, built on layers of observation, calculation, and understanding. Another theory that shapes how we measure the universe is general relativity. Einstein's description of gravity as the curvature of space-time. Massive objects bend space around them, and light follows those curves. This means light from distant galaxies doesn't travel in straight lines. It bends around clusters, gets focused by dark matter, and takes paths that depend on the distribution of mass between us, the source. Astronomers have to account for this bending, called gravitational lensing, when calculating distances. Sometimes, lensing helps, magnifying distant objects and making them easier to see. Other times, it complicates things, creating multiple images or distorting shapes. General relativity also tells us that space can expand, that the fabric of the universe itself can stretch. This expansion isn't something happening in space. It's space itself growing, carrying galaxies along with it. That's why distant galaxies can recede faster than light without breaking any physical laws. They're not moving through space faster than light. The space between us and them is expanding, and there's no speed limit on that. All of these theories, parallax, standard candles, redshift, relativity, they're different ways of approaching the same question. How big is the universe? How far away are the things we see? And while each method has limits, together they paint a consistent picture. The universe is vast, larger than any single method could measure, but not so large that we can't describe it. We've built a scaffold of theories and observations that reaches from Earth to the edge of visibility. And the view from that scaffold is 93 billion light years across. It's a testament to human ingenuity that we can measure something so large using tools so small. Telescopes, mathematics, light, these are the instruments we have, and they're enough. Not perfect, not without uncertainty, but enough to map the cosmos, to give us numbers that capture, however imperfectly, the scale of everything. So when you hear that the universe is 93 billion light-years across, remember that number is built on theories, on careful observation, on centuries of thought and measurement. It's not a guess. It's the result of multiple methods, all pointing in the same direction, all agreeing, within margins of error, that this is how big the visible universe is. Theories might be refined, while the number might shift slightly as techniques improve. The basic truth remains. The universe is vast. We've measured it, and the different ways we've measured it all tell the same story. When you want to measure something close, you use a ruler, a tape measure, maybe your own footsteps. But when the thing you're measuring is billions of light years away, those tools don't work. You can't send a probe to the edge of the universe. You can't stretch anything across that distance. All you have is light, ancient photons that have traveled across space and time to reach you. And somehow, from those faint signals, astronomers have learned to measure the immeasurable. Light is both the messenger and the measuring tape. Every photon carries information about where it came from, how long it's been traveling, and what it passed through along the way. By catching that light, analyzing it, and reading its story, we can calculate distances that no physical ruler could ever span. It's a patient process, built on observation, mathematics, and clever reasoning. And it all starts with the simple fact that light travels at a constant speed. The speed of light, roughly 300,000 kilometers per second, is the foundation of cosmic measurement. It's fast enough that on Earth, light seems instantaneous. You flip a switch and the room brightens without delay. But across cosmic distances, that speed becomes finite, measurable. Light from the moon takes just over a second to reach us. Light from the sun takes 8 minutes. Light from the nearest star, Proxima Centauri, takes 4 years. That delay turns speed into distance, time into space. When astronomers look at a distant galaxy, they're not seeing it as it is now. They're seeing it as it was when the light left millions or billions of years ago. The farther the galaxy, the older the light. In this way, looking outward is also looking backward, and distance becomes a measure of both, space and time. A galaxy 10 billion light-years away is also 10 billion years in the past, a snapshot from when the universe was younger, smaller, and filled with different structures. The first step in measuring cosmic distances is finding something whose distance you already know or can calculate. For nearby stars, that's parallax, the apparent shift in position when viewed from different points in Earth's orbit. By measuring that tiny shift, astronomers can triangulate the distance using geometry. It's the same principle surveyors use on Earth, just applied to the sky. Parallax works well for stars within a few thousand light years, close enough that the shift is detectable with precise instruments. Beyond parallax range, astronomers turn to standard candles, objects whose true brightness is known. The idea is simple. If you know how bright a light bulb should be, and you can measure how bright it looks from where you stand, you can calculate how far away it is. The dimmer it appears, the farther it must be. In astronomy, certain stars and stellar events serve as these cosmic light bulbs, shining with predictable luminosity. Cepheid variable stars were the first widely used standard candles. These stars pulse in brightness with clockwork regularity, swelling and shrinking as they cycle between brighter and dimmer states. Henrietta Swan Leavitt, working at Harvard College Observatory in the early 1900s, discovered that the period of a Cepheid's pulsation is directly related to its true luminosity. A star with a longer period is intrinsically brighter. By measuring how long a Cepheid takes to pulse, you know its true brightness. By measuring how bright it appears, you calculate its distance. Edwin Hubble used Cepheids to measure the distance to Andromeda, finding stars within that faint nebula and tracking their pulsations over weeks and months. The calculations showed Andromeda was nearly 1 million light-years away, far beyond the Milky Way's edges. That single measurement transformed our understanding of the universe, proving that other galaxies existed and establishing a method for reaching them with light. For galaxies too distant for individual Cepheids to be seen, astronomers use brighter standard candles. Type Ia supernovae are among the most useful. These occur when a white dwarf star, the collapsed core of a sun-like star, accretes matter from a companion until it reaches a critical mass and explodes. Because that mass threshold is always the same, the explosions have the same intrinsic brightness. They're so luminous that they outshine entire galaxies for weeks, making them visible across billions of light-years. By measuring the apparent brightness of a Type Ia supernova and comparing it to the known true brightness, astronomers calculate its distance. This method has been used to measure galaxies halfway across the observable universe, revealing not only their distances, but also the expansion history of the cosmos. In the late 1990s, observations of distant supernovae led to the discovery that the universe's expansion is accelerating, driven by some mysterious force now called dark energy. Another tool for measuring cosmic distances is redshift, the stretching of light caused by the expansion of space. When a galaxy moves away from us, or when space itself expands between us, the wavelengths of light get stretched toward the red end of the spectrum. The amount of stretching reveals how fast the galaxy is receding, and because the expansion of the universe is predictable, at least statistically, that recession speed can be converted into distance using Hubble's law. Hubble's law states that the farther away a galaxy is, the faster it's moving away from us. This isn't because galaxies are racing through space, but because space itself is expanding. On average, galaxies that are twice as far away recede twice as fast. By measuring the redshift of a galaxy's light, astronomers can estimate its distance. This method works for galaxies billions of light-years away, far beyond the reach of Cepheids or supernovae. But redshift isn't perfect. It measures recession speed, which depends on the expansion rate of the universe. That rate, the Hubble constant, isn't precisely known. Different methods give slightly different values, and the debate continues. Still, redshift provides a consistent way to rank galaxies by distance, even if the exact numbers carry some uncertainty. The investigation also involves mapping the distribution of galaxies across the sky. Large surveys, like the Sloan Digital Sky Survey, capture images and spectra of millions of galaxies, measuring their positions and redshifts. From that data, astronomers create three-dimensional maps showing how galaxies cluster, how they're arranged into filaments and voids, and how the cosmic web stretches across space. These maps don't just show distances, they show structure, revealing the universe's large-scale architecture. Light carries other information too. Its spectrum, the rainbow of colours it contains, reveals the chemical composition of stars and galaxies. Certain elements absorb or emit light at specific wavelengths, leaving fingerprints in the spectrum. By studying those fingerprints, astronomers learn what galaxies are made of, how old their stars are, and how fast they're forming new ones. This information helps refine distance estimates and builds a richer picture of cosmic history. Gravitational lensing adds another layer. Massive objects, like galaxy clusters, bend light passing near them, distorting the images of more distant galaxies behind them. By studying these distortions, astronomers can measure the mass of the lensing object and refine the distances to the background galaxies. Lensing also magnifies distant objects, allowing astronomers to see galaxies that would otherwise be too faint. It's like using the universe's own gravity as a telescope, a natural tool that extends our reach. All of these methods, parallax, Cepheids, supernovae, redshift, lensing, they form a chain. Each one builds on the one before it, extending our reach a little farther. The chain is only as strong as its weakest link, which is why astronomers constantly test and refine their measurements. When different methods agree, confidence grows. When they disagree, it signals that something needs adjustment, that our understanding isn't complete. The investigation into the universe's size is ongoing. New telescopes, like the James Webb Space Telescope, are looking deeper into space and farther back in time, finding galaxies that existed when the universe was only a few 100 million years old. Each discovery refines our understanding, adjusts the numbers, and pushes the boundaries of what we can see. The investigation never ends because the universe keeps revealing itself, layer by layer, photon by photon. And through it all, light remains the constant. It's the messenger that crosses the void, the signal that carries information across billions of years, the thread that connects us to the farthest reaches of the cosmos. Without light, we'd be blind to everything beyond our immediate surroundings. With it, we can measure the universe, map its structure, and trace its history back to the beginning. So when you think about the size of the universe, remember that every number comes from light, from photons captured by telescopes, analyzed by instruments, and interpreted by minds that refuse to accept mystery without investigation. Light is our measuring tape, our guide, our connection to the vastness, and it's enough. The number arrived slowly, built over decades of observation, calculation, and refinement. 93 billion light years. That's the diameter of the observable universe, the sphere of space from which light has had time to reach us since the beginning. It's not a guess or an estimate. It's a measurement, grounded in data, confirmed by multiple methods, and consistent with everything we know about cosmic expansion. But how do you arrive at such a number? How do you measure something so large that even light, travelling at its maximum speed, takes billions of years to cross it? The answer lies in combining observations with theory, in using what we can see to infer what we cannot. The data comes from telescopes pointed at the sky, capturing light from distant galaxies and analysing it for clues about distance, age, and motion. The first piece of data is the age of the universe, approximately 13.8 billion years. This number comes from multiple sources. The cosmic microwave background, the faint afterglow of the Big Bang, shows patterns that encode the universe's age. The oldest stars in globular clusters provide another check. Their age is calculated from models of stellar evolution. The expansion rate, measured through observations of distant galaxies, gives a third line of evidence. These converge on the same answer. The universe has been expanding for about 13.8 billion years. If light has been travelling for that long, you might think the edge of the observable universe should be 13.8 billion light years away. But that's where the data gets more interesting. Space itself has been expanding during all that time, carrying galaxies farther apart. A galaxy whose light has been travelling for 13 billion years is no longer 13 billion light years away. It's much farther because the space between us and it has stretched while the light was in transit. To calculate the current distance, astronomers use models of cosmic expansion. These models take into account the rate at which space is growing, how that rate has changed over time, and the effects of dark energy, the mysterious force that's accelerating the expansion. By integrating these factors, they arrive at a current distance of about 46 billion light-years in any direction from Earth. Double that to span the full diameter, and you get 93 billion light-years. This number is based on observations of the cosmic microwave background, the oldest light we can see. That light was emitted when the universe was only 380,000 years old, when space had cooled enough for atoms to form and photons to travel freely. The sources of that light, the hot plasma that filled the early universe, are now about 46 billion light-years away due to expansion. That's the edge of the observable universe. The horizon beyond which we cannot see because light from farther regions hasn't had time to reach us yet. The data also includes measurements of the Hubble constant, the rate at which the universe is expanding. This rate is usually expressed in kilometers per second per megaparsec, a unit that describes how fast galaxies are receding for every unit of distance. Current measurements put the Hubble constant at around 67 to 70 kilometers per second per megaparsec, though different methods give slightly different values. This rate tells us how quickly space is stretching, which in turn affects how we calculate distances. Redshift measurements provide another layer of data. When light from a distant galaxy is stretched by the expansion of space, its wavelength increases, shifting toward the red end of the spectrum. The amount of redshift, expressed as a number called Z, tells us how much the universe has expanded since the light was emitted. A galaxy with a redshift of Z equals 1 has light that's been stretched by a factor of 2, meaning the universe has doubled in size since that light began its journey. The highest redshifts observed are around Z equals 10 or more, corresponding to galaxies seen when the universe was less than 5% of its current age. By combining redshift with models of expansion, astronomers can calculate the current distance to any galaxy. The data shows that the most distant galaxies, those with the highest redshifts, are now about 46 billion light-years away. These are the galaxies that define the edge of the observable universe, the farthest regions from which light has reached us. The cosmic microwave background adds precision. Satellites like WMAP and Planck have mapped this ancient light in exquisite detail, measuring tiny temperature fluctuations across the sky. These fluctuations encode information about the universe's composition, its geometry, and its expansion history. From this data, cosmologists derive not only the age of the universe, but also its size, its curvature, and the amounts of ordinary matter, dark matter, and dark energy it contains. The data reveals that the universe is remarkably flat, meaning its geometry is Euclidean on large scales. If it had significant curvature, distances would behave differently, and the size of the observable universe would change. But measurements show that curvature is zero or very close to it within observational limits. This flatness is consistent with the 93 billion light-year diameter, confirming that the models are on the right track. Another piece of data comes from large-scale galaxy surveys. Projects like the Sloan Digital Sky Survey have mapped millions of galaxies, measuring their positions, distances, and velocities. This data shows how galaxies cluster into filaments and walls, separated by vast voids. The distribution follows patterns predicted by models of cosmic structure formation, where tiny density fluctuations in the early universe grew over billions of years into the web of galaxies we see today. The scale of this web, stretching billions of light-years, is consistent with the overall size of the observable universe. Supernovae observations add further confirmation. By measuring the brightness and redshift of Type Ia supernovae in distant galaxies, astronomers have traced the expansion history of the universe. The data shows that expansion was slowing down for the first several billion years. as gravity pulled galaxies together. But about 5 billion years ago, the expansion began to accelerate, driven by dark energy. This acceleration affects how we calculate distances, and it's baked into the 93 billion light-year number. The data also includes uncertainties. The Hubble constant isn't known exactly. Different methods give values that differ by a few percent, a discrepancy called the Hubble tension. This affects distance calculations, introducing a small range of possible values for the size of the observable universe. 93 billion light-years is the central estimate, but it could be a few billion light-years smaller or larger depending on which measurements you trust. There's also the question of what lies beyond the observable universe. The data can't tell us that directly because light from those regions hasn't reached us, but the models suggest that space continues, possibly infinitely. The observable universe is just the part we can see, a bubble centered on Earth, defined by how far light has had time to travel. Beyond that bubble, there are likely more galaxies, more structures, more space, all inaccessible to observation, but implied by the uniformity and flatness we see within our horizon. The number 93 billion light-years is the culmination of all this data. It's not a single measurement, but a synthesis, a combination of observations, models, and calculations that all point toward the same conclusion. The observable universe is vast, larger than early astronomers ever imagined, yet finite in what we can see. The data gives us the boundaries, the horizon beyond which light cannot reach, and within that horizon, a cosmos filled with 2 trillion galaxies, each one a system of billions of stars. What's remarkable is how consistent the data is. Different methods, different observations, different instruments all converge on similar numbers. The age of the universe, the expansion rate, the distance to the cosmic microwave background, the distribution of galaxies, they all fit together into a coherent picture. That consistency gives confidence that the number is real, that 93 billion light-years is not just a calculation but a description of something that actually exists. And yet, even with all this data, the number remains abstract. 93 billion light-years doesn't feel real the way 10 meters or 100 kilometers does. It's too large to picture, too vast to hold in the mind. But the data doesn't care about intuition. It simply records what is, translates it into numbers, and hands us the result. The universe is this big. The data says so. And whether we can fully grasp it or not, the measurement stands. So when you hear 93 billion light-years, remember that it's built on centuries of observation, decades of calculation, and layers upon layers of data. It's the best answer we have, refined by every new telescope, every new measurement, every new insight into how the cosmos works. The data points toward vastness, and the vastness, incomprehensible as it feels, is real. The observable universe, 93 billion light-years across, is not the entire universe. It's only the part we can see, the bubble of space from which light has had time to reach us. Beyond that horizon, space continues. Perhaps it goes on forever, stretching infinitely in all directions. Perhaps it wraps around itself in ways we can't detect. Perhaps there are regions with different properties, different structures, even different physical laws. We don't know, because the light from those regions hasn't arrived and may never arrive. This is the deeper mystery. Not how big the observable universe is, we've measured that, but how big the whole universe is. The totality of everything, the cosmos beyond the horizon. And this question, unlike the ones about what we can see, doesn't have a data-driven answer. It has theories, possibilities, educated guesses, but the truth lies beyond our reach, hidden by the limits of light and time. The first thing to understand is why there's a horizon at all. Light travels at a finite speed, and the universe has a finite age. Those two facts combine to create a boundary. Light from regions farther than 46 billion light-years away hasn't had time to reach us yet. It's still traveling, crossing space at 300,000 kilometers per second, but the universe isn't old enough for that light to have arrived, and because space is expanding, some of that light never will arrive. Distant regions are receding faster than light can close the gap, not because they're moving through space that fast, but because space itself is stretching. This creates a horizon, not a physical edge, but a limit of visibility. Beyond it, the universe presumably continues. Galaxies still shine, stars still burn, space still stretches. But we can't see any of it, and we never will. The horizon is permanent, set by the laws of physics, and no telescope, no matter how powerful, can look beyond it. So the question becomes, what's out there? And here's where the mystery deepens. The observable universe looks remarkably uniform. In every direction we look, we see roughly the same number of galaxies, the same large-scale structures, the same cosmic web of filaments and voids. The cosmic microwave background, the ancient light from the early universe, is nearly the same temperature everywhere, varying by only 1 part in 100,000. This uniformity suggests that the universe beyond the horizon is probably similar to what we see within it. If the universe is infinite, and if it's uniform on large scales, then everything we see within the observable universe, every galaxy, every star, every structure, repeats endlessly beyond the horizon. Not just similar structures, but exact duplicates. In an infinite universe, with finite arrangements of matter, every possible configuration must occur, and must occur infinitely many times. That means somewhere impossibly far away, there's another Milky Way, another solar system, another Earth, another you, living a life identical to yours, or slightly different in one detail or another. This isn't science fiction. It's a logical consequence of infinity combined with finite possibilities. If space goes on forever, and matter can only arrange itself in so many ways, then repetition is inevitable. Somewhere, there's a planet identical to Earth, down to the last atom. Somewhere, there's a version of you reading these exact words at this exact moment. Somewhere, there's a version where you made a different choice this morning and your day unfolded differently. Infinity doesn't just allow these possibilities, it requires them. But infinity is a big if. We don't know whether the universe is truly infinite. It could be finite but unbounded, like the surface of a sphere. If you travel far enough in one direction, you'd eventually return to where you started. Not because you hit an edge, but because space curves back on itself. In such a universe, there would be no duplicates, no infinite repetitions, just a large but finite amount of space containing a finite number of galaxies. Current measurements suggest the universe is flat or very close to it, which is consistent with being infinite. But measurements have error bars, and a tiny amount of curvature could exist without us detecting it. So the question remains open. Is the universe infinite, or is it just very, very large? We may never know, because the evidence lies beyond the horizon, inaccessible to observation. There's also the possibility of a multiverse, not just more space beyond the horizon, but entirely separate universes, each with its own properties. Some theories of inflation, the rapid expansion that occurred in the first fraction of a second after the Big Bang, suggest that different regions of space could have inflated differently, creating bubble universes disconnected from each other. Our observable universe would be one bubble, and beyond it, in regions we can never access, other bubbles might exist, each one a universe in its own right. These other universes might have different physical constants, different forces, different particles. In some, stars might not form. In others, atoms might not hold together. Our universe seems finely tuned for complexity, for stars and planets and life. But that might just be selection bias. We exist in this universe because it allows us to exist. Other universes, if they exist, might be sterile, empty, lifeless. We'd never know, because they're forever beyond reach. The multiverse is speculative, not proven, but it arises naturally from some of our best theories. If inflation happened, if quantum mechanics works the way we think it does, then other universes might be inevitable. But testing the idea is nearly impossible, because by definition, other universes are causally disconnected from ours. No signal can pass between them. No observation can confirm or deny their existence. They remain in the realm of theory, a deeper mystery layered on top of the mystery of what lies beyond our cosmic horizon. Even within the observable universe, there are mysteries. Dark matter makes up most of the mass, yet we don't know what it is. Dark energy drives the accelerating expansion, yet we don't know its nature. These unknowns remind us that even what we can see, even what we've measured, holds secrets. The universe is not fully understood, not fully explained, and beyond the horizon, the mysteries only deepen. There's also the question of what was before the Big Bang, if before even makes sense in that context. Time itself might have begun with the Big Bang, in which case there was no before. Or time might be part of a larger structure, a multiverse or cyclic cosmos where universes are born, expand, and die, only to be replaced by new ones. These ideas push the limits of physics and philosophy, asking not just how big the universe is, but whether it's the only one, and whether it has always existed or had a beginning. The deeper mystery is humbling because it reminds us of the limits of knowledge. We can measure what's within the horizon. We can build models, test theories, and refine our understanding. But beyond a certain point, observation fails. The universe might be infinite. It might be finite. It might be one of many. We might live in a cosmos far larger than we can ever confirm, or we might be part of something even stranger, a multiverse of possibilities where every variation exists somewhere. And perhaps that's okay. Perhaps the mystery is part of the beauty. The universe reveals itself up to a point, then draws a curtain, leaving the rest to imagination. We can wonder about what lies beyond, speculate, theorize, dream, but we can't know, not with certainty. The horizon is both a limit and a gift, a boundary that defines what we can see, but also hints at vastness beyond. So when you think about the size of the universe, remember that 93 billion light years is only the beginning. Beyond that, space might continue forever, or it might curve back, or it might branch into other universes entirely. The deeper mystery isn't about numbers, it's about possibility, about the humbling realization that the cosmos might be larger, stranger, and more complex than we'll ever be able to confirm. And that mystery, unsolved and perhaps unsolvable, is part of what makes the universe so endlessly fascinating. For a long time, people assumed the universe was static, eternal, unchanging. The stars moved in their regular patterns, the planets followed their orbits, and the sky looked the same generation after generation. It seemed natural to think that the cosmos as a whole was stable, that it had always been as it is. and would remain that way forever. But in the early 20th century, observations began to suggest something different, something that would change everything. The universe wasn't static, it was growing. The first hints came from measurements of distant galaxies. In the 1920s, astronomers noticed that the light from most galaxies was redshifted, stretched toward longer wavelengths. At first, this was puzzling. Why would galaxies be moving away? And why would the farther ones be moving faster? Edwin Hubble, studying galaxies across the sky, found a pattern. The redshift increased with distance. Galaxies twice as far away receded twice as fast. This wasn't random motion. It was systematic, universal, as if the entire cosmos was expanding. The implication was profound. If galaxies are moving apart now, they must have been closer together in the past. Trace the expansion backward, and you arrive at a moment when everything was compressed into an incredibly small, hot, dense state. This was the beginning, the origin of space and time, the event we now call the Big Bang. The universe wasn't eternal. It had a starting point, and it had been growing ever since. This was the turning point, the moment when our understanding of the cosmos shifted from static to dynamic. The universe has a history. It was born, it grew, and it continues to grow. The sky we see tonight is not the same sky that existed 1 billion years ago. Space has stretched. Galaxies have drifted apart. The universe has changed, and it's still changing right now, even as you rest. The expansion isn't like an explosion, where matter flies outward through space. It's more subtle. Space itself is stretching, carrying galaxies along with it. Imagine dots on the surface of a balloon. As you inflate the balloon, the dots move apart, not because they're sliding across the surface, but because the surface itself is expanding. Galaxies work the same way. They're not racing through space, they're embedded in space, and the space between them is growing. This expansion happens everywhere, at all times. Right now, between you and the nearest galaxy, space is stretching. Between that galaxy and the next, more stretching. On large scales, this adds up to enormous velocities. Galaxies millions of light years away recede at thousands of kilometers per second. Galaxies billions of light years away recede even faster, some of them faster than light. Not because they're moving through space that quickly, but because the space itself is expanding. The turning point also revealed the age of the universe. If space has been expanding at a measurable rate, you can calculate how long it's been expanding, trace it back to the beginning, and you find that the universe is about 13.8 billion years old. That's not an arbitrary number. It's derived from observations, confirmed by multiple methods, and consistent with the oldest stars, the cosmic microwave background, and the distribution of galaxies. The universe had a beginning, and we know approximately when. But the story doesn't end with expansion. In the late 1990s, astronomers studying distant supernovae discovered something unexpected. The universe's expansion wasn't slowing down, as they'd assumed. It was speeding up. Some mysterious force, now called dark energy, was pushing galaxies apart faster and faster. This acceleration had been going on for billions of years, and it showed no signs of stopping. The discovery of dark energy was another turning point, a twist in the story. Not only is the universe growing, it's growing faster. The implications are staggering. In the far future, the expansion will carry most galaxies beyond our horizon. They'll recede so far, so fast, that their light will no longer reach us. The observable universe will shrink, not because space is contracting, but because the objects within it are being swept away by expansion. Future civilizations, if they exist, might look up and see only the stars of their own galaxy, unaware that billions of others once filled the sky. This acceleration changes the universe's fate. For decades, cosmologists debated whether the expansion would continue forever or eventually reverse, causing the universe to collapse in a big crunch. The universe will expand forever. Galaxies will drift apart. Stars will burn out. Eventually, the cosmos will become cold, dark, and empty. A vast expanse where isolated galaxies flicker in the darkness before their last stars fade. But that future is trillions of years away. For now, the universe is still bright, still filled with galaxies, still accessible to observation. The turning point isn't about the distant future. It's about understanding the present. The universe is growing, and that growth shapes everything we see. It determines the size of the observable universe, the distances to galaxies, the age of the cosmos, and the fate of everything within it. The expansion also explains why the night sky is dark. If the universe were infinite, eternal, and static, every line of sight would eventually hit a star, and the sky would blaze with light. But because the universe is expanding and has a finite age, most of the sky is empty. Light from distant regions hasn't had time to reach us, and light from the most distant regions is so redshifted it's invisible to our eyes. The darkness of the night sky is evidence of expansion, a quiet confirmation that space is growing. The turning point from static to dynamic changed not just cosmology but philosophy. It meant the universe had a story, a beginning and an unfolding. It meant time was not infinite in the past, that there was a first moment. It meant the cosmos was not a stage for events but an active participant, growing and changing, shaping the events that occur within it. The universe wasn't a backdrop, it was part of the narrative, and it's still growing. Right now, between the time you started reading this chapter and now, space has expanded. Galaxies have moved a little farther apart. The universe has grown a little larger. The change is tiny, imperceptible on human timescales, but it's real. The cosmos is not frozen. It's alive with motion, driven by forces we're only beginning to understand. The turning point was realizing that the universe is not something fixed and eternal, but something that began, that evolved, and that continues to change. The expansion is the heartbeat of the cosmos, the rhythm that defines its past and shapes its future. And knowing that, understanding that the universe is still growing, transforms how we see it. The stars aren't just distant points of light. They're part of a living, expanding system, a cosmos in motion, carrying us all forward into a future we can barely imagine. The realization that the universe is expanding, that it's still growing, leads to a consequence that's both humbling and isolating. We live in a bubble, not a physical bubble, but a bubble of visibility, a sphere of space from which light has had time to reach us. Beyond that sphere, the universe continues, but we can't see it. The expansion of space ensures that some regions will remain forever hidden, their light unable to cross the growing distances fast enough to ever arrive. This bubble is the observable universe, 93 billion light-years across, centered on Earth not because we're special, but because the horizon is defined relative to wherever you are. If you lived in a galaxy on the other side of the observable universe, you'd have your own bubble, your own horizon, overlapping with ours, but extending into regions we'll never see. Every observer, everywhere, lives inside their own bubble of visibility. The universe we can study, the galaxies we can map, the structures we can measure, all of it is just a sample. a tiny fraction of what might exist. If the universe is infinite, then the observable universe is infinitesimally small compared to the whole. Even if the universe is finite but much larger than what we can see, we're still missing most of it. Our knowledge, comprehensive as it seems, is based on a limited view. This bubble isn't static. It's growing, but slowly. As time passes, light from more distant regions reaches us, expanding our horizon. In 1 billion years, assuming nothing else changes, we'll be able to see a little farther. But the expansion of space complicates this. While the bubble grows, distant galaxies are receding, carried away by the stretching of space. For the nearest galaxies, the bubble expands faster than they recede. We'll eventually see them more clearly. But for the farthest galaxies, the ones near the edge of the observable universe, they're receding so fast that we'll never see them as they are now. We only see them as they were billions of years ago. And then there are the galaxies beyond the horizon, the ones we can't see yet. Into view, eventually, their light finally reaching us after travelling for billions of years. But others, the ones far enough away, are receding faster than light can travel. Their light will never reach us. They're beyond the horizon permanently, forever outside our bubble. Space is expanding so quickly between us and them that the gap keeps growing, faster than light can close it. This creates a strange reality. There are galaxies out there, shining brightly, filled with stars and perhaps life, but they're invisible to us, not because they're too faint, but because the universe's structure prevents their light from arriving. We're causally disconnected from them. No signal, no light, no information can pass between us. They might as well not exist, at least as far as our observations are concerned. The bubble also means we're seeing the universe at different times in different directions. When we look at a galaxy 10 billion light years away, we see it as it was 10 billion years ago. When we look in the opposite direction, same distance, same age, every direction shows us the past, layered across the sky, with the most distant objects appearing as they were when the universe was young. The bubble is not just a spatial boundary, it's a temporal one, a limit on how far back in time we can see. The cosmic microwave background, the faint afterglow of the Big Bang, marks the edge of this temporal bubble. It's the oldest light we can observe, emitted when the universe was only 380,000 years old. Before that, the universe was opaque, filled with hot plasma that scattered photons. No light from earlier times can reach us. The cosmic microwave background is the wall of visibility, the farthest we can see in time. Beyond it, there's no light to observe, only theory and inference. Living in a bubble has consequences for what we can know. The universe beyond our horizon might be very different from what we see. It might have different structures, different densities, even different physical constants. Or it might be uniform, the same everywhere, just like our bubble. We can't know for sure because the evidence lies beyond reach. Our theories assume uniformity, that the universe looks the same everywhere on large scales. But that assumption is based on the portion we can see. It's an extrapolation, not a confirmed fact. The bubble also shapes the future. As the universe continues to expand and accelerate, driven by dark energy, distant galaxies will recede beyond our horizon. In hundreds of billions of years, most of the galaxies we see today will have vanished from view. Their light redshifted into invisibility, their images frozen at the moment they cross the horizon. Future observers, if they exist, will live in a lonelier universe, one where fewer galaxies are visible, where the sky is darker, emptier. Eventually, in the far future, Only the galaxies bound to us by gravity, our local group, will remain visible. Everything else will have drifted beyond the horizon. Future astronomers won't be able to see distant galaxies. They won't be able to measure cosmic expansion. They might not even know the universe had a Big Bang, because the evidence, the redshifts, the cosmic microwave background will have faded beyond detection. They'll live in a smaller bubble, isolated, unaware of the vastness that once surrounded them. This is the consequence of expansion. It's not just that the universe is large, it's that the largeness is temporary, at least in terms of what we can observe. We live in a special time, a cosmic era, when the universe is old enough to have formed galaxies and stars, but young enough that most of them are still visible. We can see the history of the cosmos written in the sky, layer upon layer of light from different eras. That window won't last forever. It's already closing, slowly, as expansion carries distant galaxies away. Living in a bubble also means we're connected to everything within it. The light from distant galaxies, the cosmic microwave background, the structure of the cosmic web, all of it is part of our bubble, part of what defines our observable universe. We're not separate from it. We're embedded in it, part of the same network of causality, the same flow of information. Everything within the bubble can, in principle, affect us. Everything beyond it cannot. This creates a kind of cosmic horizon, a boundary not of space but of influence. We can never visit galaxies beyond the horizon. We can never receive signals from them. They're forever out of reach, not because of distance alone, but because the expansion of space ensures the gap keeps growing. We're confined to our bubble, not by walls, but by the structure of space-time itself. And yet, the bubble is vast, 93 billion light-years across, filled with 2 trillion galaxies, each one a system of billions of stars. The observable universe is only a fraction of the whole, but that fraction is still larger than we can fully explore, larger than we'll ever visit, larger than our minds can comfortably hold. We live in a bubble, yes, but it's a bubble of staggering scale, a cosmos in miniature that still holds more wonders than we'll ever count. So the consequence of living in a bubble is not limitation, not really. It's perspective. It's the understanding that what we see is not everything, that beyond our horizon lies more, possibly infinitely more. But what we see is enough. It's more than enough. It's a universe. Understanding the size of the universe doesn't just add a number to our knowledge. It changes how we see ourselves, how we think about our place, how we interpret the meaning of existence itself. When the universe was thought to be small, humans could imagine being central, significant, perhaps even the purpose for which everything was created. But once the scale became clear, once we realized the cosmos stretches 93 billion light-years and beyond, that sense of centrality dissolved. We're not at the center. We're not even close. And that realization has an impact that ripples through science, philosophy, and daily life. The first impact is on our sense of importance. In a universe this large, with 2 trillion galaxies and countless stars, Earth becomes almost invisible. We're a small planet orbiting an average star in the outer regions of an ordinary galaxy. Nothing about our location is special. Nothing about our sun makes it stand out. We're one dot among trillions, a mote of dust in a cosmic ocean. That smallness can feel diminishing, as if our lives, our struggles, our achievements don't matter in the grand scheme. But there's another way to see it. The universe's size doesn't erase meaning. It changes the scale of meaning. What happens on Earth might not matter to distant galaxies, but it matters here. It matters to us. The fact that the cosmos is vast doesn't make love less real, beauty less striking, or kindness less important. The universe doesn't care, but we do. And in a universe that doesn't assign meaning, we're free to create it ourselves. The size also impacts how we think about life elsewhere. With so many stars, so many galaxies, the odds that Earth is the only place with life seem vanishingly small. Statistically, there should be other worlds, other species, other civilizations scattered across the cosmos. The universe's vastness makes life seem probable, even inevitable. Yet, the distances are so large that we might never meet anyone else. Two civilizations could exist in the same galaxy and never know about each other, separated by thousands of light years and millions of years of history. The universe is big enough to hold countless forms of life, but also big enough to keep them isolated, alone in their own bubbles of visibility. This creates a strange paradox. We're probably not alone, but we might always feel alone. The universe could be teeming with life, yet the distances ensure that contact is rare, perhaps impossible. The vastness connects us to the possibility of others, while simultaneously isolating us from them. It's a loneliness built into the structure of space-time itself, a consequence of light's finite speed and space's expansion. The size of the universe also impacts how we think about time. 93 billion light-years is not just a spatial measurement, it's also a temporal one. Looking outward is looking backward. The farthest galaxies we see appear as they were over 13 billion years ago, when the universe was young. To observe the cosmos is to observe history, to see the past laid out across the sky. The universe's size gives us access to its entire lifespan, from the first galaxies forming a few 100 million years after the Big Bang, to the mature structures we see nearby today. This means the universe is not just big in space, it's big in time. 13.8 billion years of history, all visible if we look far enough. That temporal scale dwarfs human history. Civilization has existed for a few thousand years, our species for a few 100,000, life on Earth for a few billion. The universe is older than all of it, and it will continue long after Earth is gone. The size in time is as humbling as the size in space, a reminder that we're brief visitors in a cosmos that began before us and will end long after. Knowing the size of the universe shapes every question we ask. How did galaxies form? Why is the universe expanding? What is dark matter? What is dark energy? These questions only make sense in the context of cosmic scale. The answers require understanding distances, ages, and structures that span billions of light years and billions of years. Science had to grow to match the universe's size, developing tools and theories that could reach across that vastness. Philosophy also feels the impact. If the universe is this large, and if it might be infinite, what does that say about existence? Are there infinite versions of us, infinite Earths, infinite variations on every possible event? If so, what does that mean for free will, for uniqueness, for identity? These are not just abstract questions. They touch on how we understand ourselves and our place in reality. The size of the universe doesn't answer these questions, but it reframes them, making them more complex and more urgent. The impact also extends to how we value things. In a universe this large, scarcity becomes relative. There are more stars than grains of sand, more planets than people who have ever lived. Resources that seem limited on Earth might be abundant elsewhere. The perspective shifts from local scarcity to cosmic abundance, changing how we think about what's rare and what's common. And yet, paradoxically, the vastness makes Earth more precious, not less. Yes, there might be other planets with life, But this one is ours. This is the only place we know where life exists. That makes it irreplaceable, worth protecting, worth caring for. There's also a psychological impact. Knowing the universe is 93 billion light years across can be overwhelming. It's too big to picture, too vast to hold in the mind. Some people find that overwhelming, even frightening. The immensity presses down, making them feel small, insignificant, lost. Others find it calming, a reminder that their worries are temporary, their troubles fleeting. The universe doesn't care about missed deadlines or awkward conversations. It simply continues, vast and indifferent, and that indifference can be freeing. For some, the size inspires curiosity. If the universe is this large, what else is out there? What haven't we seen yet? What mysteries remain? The vastness becomes not a source of fear, but a source of wonder, an invitation to explore, to learn, to reach farther. Every question answered reveals 10 more. Every boundary pushed reveals more space beyond. The size of the universe ensures that curiosity will never run out of material. The impact is also cultural. Human cultures have always looked to the sky for meaning, for stories, for guidance. The universe's size changes those stories. We're no longer the center of creation. We're one small part of something unimaginably larger. That shift has been disorienting for many, challenging traditional narratives about humanity's place and purpose. But it's also opened new narratives, new ways of thinking about who we are and what we might become. We're small, yes, but we're also capable of understanding vastness. We're temporary, yes, but we're part of something eternal. Ultimately, the impact of the universe's size is what we make of it. The 93 billion light years don't dictate meaning. They provide context. They show us the stage on which our lives unfold, a stage so large that it makes everything else seem small. But smallness isn't the same as insignificance. We can be small and still, matter, finite and still meaningful, brief and still important. The universe's size doesn't diminish us. It invites us to find meaning in the midst of vastness, to carve out purpose in a cosmos that doesn't assign it for us. How size changes everything, then, is not about erasing what matters. It's about expanding perspective, about seeing ourselves as part of a much larger whole. The universe is vast. We are small. And somehow, both of those things are okay. More than okay. They're part of the same story, the same quiet unfolding that includes everything from galaxies to thoughts, from light years to heartbeats. Size changes everything, but it doesn't change what's essential. We're still here. We still feel. We still wonder. And in a universe this big, that's extraordinary. Behind every measurement of the universe, behind every calculation that stretches across billions of light years, there are people. Not abstract minds or distant authorities, but human beings who looked up at the night sky and refused to accept mystery without trying to understand it. The story of measuring the universe is as much about these people as it is about the cosmos itself. Their curiosity, their persistence, their willingness to spend lifetimes chasing questions with uncertain answers. These are what transformed our understanding from a small, enclosed cosmos to one that stretches beyond imagination. Henrietta Swan Leavitt never set foot in a major observatory. She worked at Harvard College Observatory in the early 1900s, one of many women employed as computers, analyzing photographic plates of stars. The work was meticulous, repetitive, often overlooked. But Leavitt noticed something others had missed. While studying Cepheid variable stars in the Magellanic Clouds, she found a relationship between their pulsation period and their brightness. The longer a Cepheid took to pulse, the brighter it truly was. This simple pattern became the key to measuring cosmic distances, the first reliable method for reaching beyond the Milky Way. Leavitt never received widespread recognition during her lifetime. She died young, at 53, before her discovery's full impact became clear. But her work laid the foundation for everything that followed. Edwin Hubble, working at Mount Wilson Observatory in California in the 1920s, used Leavitt's discovery to measure the distance to Andromeda. He identified Cepheids within that faint nebula, tracked their pulsations, and calculated how far away they were. The result, nearly 1 million light-years, was staggering. It meant Andromeda was not part of the Milky Way but another galaxy entirely. Overnight, the universe expanded. What had been thought to be the entirety of existence became just one island among many. Hubble's name is now attached to the space telescope that has peered deeper into the cosmos than any instrument before it. A fitting tribute to the person who first showed us just how large the universe truly is. But Hubble didn't work alone. Milton Humason, a former mule driver who became an astronomer, spent countless nights at the telescope, capturing spectra of faint galaxies. The work was exhausting, requiring long exposures in the cold darkness of the observatory dome. But Humason's observations provided the data Hubble needed to discover that the universe was expanding, that galaxies were receding, and that the farther they were, the faster they moved. Humason's persistence, his willingness to spend night after night chasing faint light, was as essential to the discovery as Hubble's analysis. Vera Rubin, studying galaxy rotation in the 1970s, found something unexpected. The outer regions of galaxies were rotating as fast as the inner regions, which shouldn't happen if only visible matter existed. The stars on the edges should be moving slower, the way outer planets in the solar system orbit more slowly than inner ones. But they weren't. Rubin's observations suggested that galaxies were surrounded by vast halos of invisible matter, something that didn't emit light but exerted gravity. This dark matter, as it came to be called, makes up most of the universe's mass. Rubin faced skepticism, especially as a woman in a field dominated by men, but her observations were solid. The data didn't lie. And eventually, the scientific community accepted that most of the universe was made of something we couldn't see. Saul Perlmutter, Brian Schmidt, and Adam Ress, working with teams of astronomers in the 1990s, studied distant supernovae to measure the universe's expansion history. They expected to find that expansion was slowing down, pulled back by gravity. Instead, they found the opposite. The expansion was accelerating. Some unknown force, now called dark energy, was pushing galaxies apart faster and faster. The discovery was so unexpected that both teams double-checked their data multiple times, suspecting error. But the result held. The universe wasn't just expanding, it was speeding up. For this discovery, all three shared the Nobel Prize in Physics in 2011. These are just a few names among thousands. There are countless astronomers, technicians, engineers, and mathematicians who contributed to measuring the universe. Some became famous, many didn't, but each one added a piece to the puzzle. A measurement here, a calculation there, a patient observation through a long night. The work was often slow, tedious, filled with uncertainty. Telescopes broke, weather interfered, funding ran out. But the people persisted because the question mattered. How big is the universe? And what does that size tell us about where we came from and where we're going? There's something deeply human about this quest. We're small creatures on a small planet, yet we've managed to measure distances so vast that light takes billions of years to cross them. We've counted galaxies we'll never visit, traced the expansion of space itself, and mapped the structure of the cosmos from our one tiny vantage point. That achievement isn't just scientific. It's a testament to what humans can do when curiosity meets patience, when questions meet persistence, when wonder meets rigor. The people who measured the dark didn't do it for fame or fortune. Most astronomers work in obscurity, their names known only to specialists. They do it because the universe is there, because the questions are worth asking, because understanding matters. They spend years analyzing data, decades building instruments, lifetimes chasing answers that might not arrive. And through that work, they've given us a gift, a map of the cosmos, a sense of scale, a picture of the universe that includes us but doesn't revolve around us. There's also humility in their work. Every measurement comes with error bars, every conclusion with caveats. The universe is 93 billion light-years across, give or take. The Hubble constant is 70 kilometers per second per megaparsec, approximately. Dark matter makes up 85% of the mass, probably. The scientists who study the cosmos know that their understanding is incomplete, that future observations might refine or even overturn current theories. They work with uncertainty built in, comfortable with not knowing everything, patient with the slow accumulation of knowledge. And they work together. No single person measured the universe. It took generations, each one building on the work of the last. Leavitt's discovery enabled Hubble's measurements. Hubble's measurements revealed expansion. The discovery of expansion led to the Big Bang Theory. The Big Bang Theory predicted the cosmic microwave background, which was later observed. Each step made the next possible. Science is cumulative, a collective human project that spans lifetimes and crosses borders. The people who measured the universe were part of something larger than themselves, contributing to a story that began before them and continues after. There's also courage in their work. Challenging established ideas is never easy. When Hubble suggested the universe was larger than the Milky Way, he faced skepticism. When scientists proposed the Big Bang, many rejected it as absurd. When dark matter and dark energy were discovered, the findings were met with resistance. But the data kept pointing in the same direction, and eventually, the scientific community adapted. The people who made these discoveries had to be willing to follow the evidence, even when it led somewhere unexpected, even when it contradicted what everyone believed. The human element reminds us that science is not abstract, not distant, not performed by machines or algorithms alone. It's done by people, by curious minds who look up and wonder, by persistent souls who spend years chasing faint signals, by communities that share data, critique each other's work, and slowly, collectively, build understanding. The universe is vast, but the effort to measure it is deeply human, rooted in the same curiosity that makes us look up on a clear night and ask what's out there. As you rest tonight, think about the people who've spent their lives measuring the dark, who've sat in cold observatory domes, who've analyzed endless streams of data, who've built telescopes and launched satellites and written equations that describe the cosmos. They did it so that you could know, so that the question of how big the universe is could have an answer. They measured the universe not just with instruments, but with time, patience, and care. And through their work, they've given us a glimpse of something vast, something beautiful, something that began long before us and will continue long after. That's the human element. That's the heart of the story. Science is often portrayed as a realm of certainty, where facts are facts and measurements are final. But the reality is more nuanced. Scientists disagree, sometimes strongly, about what the data means, how to interpret it, and what conclusions to draw. The size of the universe is no exception. While there's broad consensus on many points, there are also disagreements, tensions, and unresolved questions. These debates aren't failures of science, they're how science works, how understanding deepens through challenge, critique, and revision. One of the most prominent disagreements is about the Hubble constant, the rate at which the universe is expanding. Different methods for measuring this value give different results, and the discrepancy, known as the Hubble tension, has persisted for years. Some measurements, using the cosmic microwave background and models of the early universe, give a value around 67 kilometers per second per megaparsec. Other measurements, using observations of nearby galaxies and supernovae, give a value closer to 73. That might not sound like much, but in science, a difference of nearly 10% is significant. The Hubble tension matters because the expansion rate affects how we calculate distances, the age of the universe, and the nature of dark energy. If the rate is higher, the universe is younger than we thought, and distances are slightly different. If the rate is lower, the opposite is true. The disagreement suggests that either one of the measurement methods has a subtle error, or our understanding of the universe's expansion is incomplete. Perhaps dark energy behaves differently than we assume. Perhaps there's something we're missing about how space expands. The tension is unresolved, and scientists on both sides have checked and rechecked their work, confident in their methods but unable to reconcile the difference. This disagreement doesn't mean the size of the universe is unknown. Both values are close enough that the observable universe is still roughly 93 billion light-years across, give or take a few billion. But the tension reveals that precision is hard, that cosmic measurements are delicate, and that even our best tools and theories might be missing something. It's a humbling reminder that science is a process, not a destination, and that the map of the cosmos is always being refined. Another area of disagreement is about dark matter. Most scientists agree it exists, based on observations of galaxy rotation, gravitational lensing, and the large-scale structure of the universe. But what it is remains deeply uncertain. Some think it's a new kind of particle, something that doesn't interact with light but exerts gravity. Others propose modifications to gravity itself, suggesting that the laws of physics work differently on cosmic scales than we currently understand. These aren't just minor tweaks, they're fundamentally different explanations, and both sides have evidence supporting their views. The disagreement about dark matter affects how we interpret the universe's size and structure. If dark matter is a particle, then the universe contains vast amounts of invisible mass holding galaxies together. If it's a modification of gravity, then the visible matter we see is all there is, but it behaves in ways we don't yet understand. The debate has raged for decades, with no clear winner. Both explanations fit some observations but struggle with others. The opposition isn't about stubbornness or ego, it's about genuinely different interpretations of the same data. Dark energy creates similar tensions. We know it exists because observations show the universe's expansion is accelerating, but we don't know what it is. Some scientists think it's a property of space itself, a constant energy that arises from the vacuum. Others think it's a dynamic field, something that changes over time. Still others propose that our understanding of gravity is incomplete, that general relativity breaks down on cosmic scales and needs modification. Each explanation has strengths and weaknesses, and the scientific community is divided, waiting for more data to tip the scales. There's also disagreement about whether the universe is infinite. The measurements suggest it's flat or very close to flat, which is consistent with being infinite. But flatness doesn't prove infinity. The universe could be flat yet finite, curving back on itself in ways too subtle to detect. Some cosmologists favor infinity because it's simpler, requiring no special boundary conditions. Others favor a finite universe because infinity introduces philosophical and mathematical complications. The disagreement isn't just scientific, it's also about how we interpret the implications of our measurements, about what feels more plausible, more elegant, more consistent with other theories. The multiverse adds another layer of opposition. Some physicists and cosmologists take the idea seriously, arguing that it arises naturally from theories of inflation and quantum mechanics. Others dismiss it as untestable speculation, arguing that if something can't be observed, it's not science, but philosophy. The debate is sharp, sometimes contentious, because it touches on the boundaries of what science can and should address. If other universes exist but are forever beyond observation, does it even matter? Can we call it knowledge if we can never verify it? These questions divide the scientific community, and there's no consensus. Even the Big Bang Theory, widely accepted, has its critics. A small but vocal group of scientists argue that the universe didn't begin with a hot, dense state, but has existed in some form forever, perhaps cycling through phases of expansion and contraction. They point to certain puzzles in the Standard Model. Questions about what caused the Big Bang, what existed before it, and why the universe has the properties it does. Mainstream cosmology has answers to some of these questions, but not all, and the critics use those gaps to argue for alternative models. The opposition here is not as strong as it once was. The evidence for the Big Bang is overwhelming, but it persists, reminding us that science always has its skeptics, its questioners, its alternative voices. What's important to understand is that these disagreements don't undermine the basic facts. The universe is large, 93 billion light-years across in what we can observe. It's expanding, and has been for nearly 14 billion years. It contains galaxies, stars, planets, dark matter, and dark energy. These are agreed upon by the vast majority of scientists. The disagreements are about details, about what the data means at the edges of understanding, about how to interpret observations that don't yet fit neatly into theory. And these disagreements are healthy. They drive science forward. When scientists challenge each other, when they propose competing explanations, when they test and retest their assumptions, understanding deepens. The Hubble tension might lead to a breakthrough, a new insight into how the universe expands. The debate about dark matter might reveal new physics, new particles, or new laws of gravity. The questions about the multiverse might clarify what science can and cannot address. Opposition isn't the enemy of knowledge, it's the engine that propels it. There's also something human in these disagreements. Scientists aren't emotionless calculators. They have intuitions, preferences, and beliefs about how the universe should work. They invest years in their ideas, build careers around certain theories, and sometimes resist when data suggests they're wrong. That's not a flaw. It's part of being human. And the scientific process, peer review, replication, critique, is designed to catch those biases, to ensure that conclusions are based on evidence, not preference. The opposition also reminds us that science is ongoing. The universe hasn't revealed all its secrets. The map isn't complete. The measurements aren't final. Every answer opens new questions. Every discovery reveals new mysteries. The disagreements show us where the boundaries of knowledge are, where the work is still happening, where the next breakthroughs might come from. And in a strange way, the fact that scientists disagree is comforting. It means the questions are hard, that the universe isn't simple, that there's still so much to learn. So when you hear about the size of the universe, remember that the number comes with debates, with uncertainties, with scientists who see the data differently. That doesn't make the number less real, it makes it more honest. Science doesn't pretend to have all the answers. It offers the best answers available, tested and refined, with the understanding that better ones might come tomorrow. The opposition, the disagreements, the debates, they're not noise. They're part of the signal, part of how we inch closer to truth. Understanding the size of the universe intellectually is one thing. 93 billion light years, 2 trillion galaxies, hundreds of billions of stars in each. You can read those numbers, memorize them, repeat them, but feeling the scale, letting it sink into your body, into your bones, that's something different. That's the awakening. The moment when the vastness stops being abstract and becomes visceral, when you don't just know the universe is large, but feel it in a way that shifts something inside you. This awakening doesn't usually happen in a classroom or from reading a textbook. It happens quietly, often unexpectedly, when you're outside under the night sky and something clicks. Maybe you're lying on your back in a field, far from city lights, and the Milky Way arches overhead, dense with stars. You've seen it before, but this time you really see it. Each point of light is a sun. Some are closer, some farther, but all of them are inside our galaxy. One small neighborhood in a cosmos filled with billions of others. The realization settles over you, not as a thought, but as a feeling, a sense of being held inside something unimaginably vast. Or maybe you're looking at a photograph, one of those deep field images where a telescope pointed at what seemed like empty space for hours, gathering light. When the image is revealed, it's filled with galaxies, thousands of them, each one a faint smudge or spiral, and the patch of sky it captured is tiny, no larger than a grain of sand held at arm's length. If every patch of sky contains that many galaxies, then the universe is fuller than you imagined, denser with worlds, more crowded with possibilities. The scale hits you, not as a number, but as an emotion, something between awe and humility. The awakening can also come from smaller moments. You're walking at night and you see the moon, bright and familiar. You remember that it's about a light second away, that the light reaching your eyes left its surface just over a second ago. Then you think about the sun, 8 light minutes away, then the nearest star, 4 light years, then the star, galaxy, 100,000 light years across, then the universe, 93 billion. Each step outward is a leap, and somewhere in that progression, the scale becomes real. You're not just listing distances, you're tracing a path from the familiar to the incomprehensible, and feeling the gap between them. Feeling the scale in your bones means letting go of the need to picture everything. You can't visualize 93 billion light years. No one can, but you can feel the weight of the number, the way it presses on understanding, the way it makes everything else seem smaller by comparison. You stop trying to imagine each galaxy, each star, each light year, and instead you let the vastness wash over you, a presence that doesn't fit in the mind but settles somewhere deeper, in the gut, in the chest, in the quiet space where emotions live. There's often a moment of disorientation when the scale first becomes real. The ground beneath you feels less solid, not physically but metaphorically. You're standing on a planet that's spinning at 1,000 kilometers per hour, orbiting a star at 30 kilometers per second, moving through the galaxy at hundreds of kilometers per second, carried by the galaxy through space as the universe expands. All of that motion is invisible, unfelt, but it's real. And suddenly you're aware that you're not standing still but hurtling through space in multiple directions at once, part of a cosmic dance that never stops. Some people find this disorienting. The scale makes them feel unmoored, as if they've lost their place, their anchor. If the universe is this large, What does it mean to be here, on this small planet, living this small life? The questions press in, and there's no easy answer, no comforting platitude that makes the vastness less overwhelming. The awakening can be uncomfortable, even frightening, because it strips away the illusion that we're central, that we matter in some cosmic sense. But for others, the awakening brings peace. The scale that felt overwhelming becomes comforting. Yes, you're small. Yes, your life is brief, but you're part of something vast, something ancient, something beautiful. The atoms in your body were forged in stars. The light you see tonight left distant galaxies billions of years ago. You're not separate from the universe. You're woven into it, part of its fabric, a temporary pattern in an ongoing story. That connection, that belonging, can soften the edges of existential dread. The vastness holds you, not in a personal way, but in the way a river holds a drop of water, carrying it forward, part of the flow. The awakening also changes how you see time. When you feel the scale of the universe, you feel the scale of its age. 13.8 billion years. Long enough for galaxies to form, for stars to be born and die, for planets to cool and warm and cool again, for life to emerge and evolve. Your lifetime, even all of human history, is a blink against that timeline. But it's not insignificant. It's the blink in which consciousness arose, in which a species looked up and asked how big the universe is and found answers. The brevity doesn't erase the moment. It sharpens it, makes it precious. There's also an awakening to possibility. If the universe is this large, then the odds that we're alone seem small. Somewhere out there, perhaps, other beings are looking up at their sky, asking the same questions, feeling the same awe. The vastness that isolates us also connects us to that possibility, to the idea that consciousness might not be unique, that we're part of something larger than our planet, our species, our small corner of space. The awakening opens the mind to what might be, even if we'll never know for sure. Feeling the scale in your bones doesn't require telescopes or equations. It requires stillness, openness, a willingness to let the vastness in. It happens when you stop trying to control the feeling and just let it be. You're small, the universe is large, and somehow both of those truths can coexist without diminishing either. The awakening is not about understanding everything. It's about accepting that you don't, that you can't, and that that's okay. The universe is larger than comprehension, and you're part of it anyway. Some nights, after the awakening, you'll look up and feel it again. The stars won't just be points of light. They'll be suns, distant and ancient, part of a cosmos stretching farther than thought. The feeling will settle over you, gentle and enormous at once, a reminder that you're here, now, inside something vast. And in that moment, the scale won't be a burden. It'll be a gift, a perspective that makes everything else feel lighter, more manageable, more real. The awakening is personal. It happens differently for everyone. But once it happens, once you've felt the scale, you can't unfeel it. The universe remains large even when you're not thinking about it. The vastness persists, and that persistence becomes part of how you move through the world. A quiet background hum that says you're small, you're brief, and you're part of something immense. That's the awakening. That's what it means to feel the size of the universe, not just in your mind, but in your bones. After all the measurements, all the calculations, all the observations that give us 93 billion light years as the size of the observable universe, there's one more possibility to consider, one more layer that stretches understanding even further. The universe we can see, vast as it is might only be a tiny fraction of something much larger. Not just larger, but truly infinite, without end, without boundary, stretching forever in all directions. This isn't speculation. It's a serious possibility suggested by the data, by the geometry of space, by what we've learned about how the cosmos is structured. The revelation begins with the shape of the universe. Space can curve, like the surface of a sphere or a saddle, or it can be flat, like an infinite plane. Measurements of the cosmic microwave background, that ancient light from the early universe, show that space is flat or very close to it. The curvature, if it exists at all, is too small to detect with current instruments. Flatness is consistent with an infinite universe. If space is flat and extends in all directions, there's no reason for it to end. It could simply go on forever. Infinity is a strange concept because we never encounter it in daily life. Everything we know has limits. Roads end, books have last pages, lives finish. Even the observable universe, 93 billion light-years across, is finite. But infinity doesn't play by the same rules. It has no edge, no final number, no place where you could stand and say this is the end. It's not just very large, it's qualitatively different, a category that breaks the usual logic of size. If the universe is infinite, then certain consequences follow. One is that everything repeats. Matter can only arrange itself in a finite number of ways. There are only so many configurations of atoms, so many possible galaxies, so many ways stars can form and planets can orbit. In a finite region of space, those possibilities play out once or a few times. But in an infinite universe, every possibility occurs infinitely many times. That means somewhere, impossibly far away, there's another Milky Way galaxy, another solar system, another Earth, another you. This isn't metaphor, it's mathematics. If space is infinite and matter is distributed roughly uniformly, then the same patterns must repeat. The odds of finding an exact duplicate of any region, no matter how specific, approach certainty as you extend the search across infinite space. There are infinite copies of you out there, living lives identical to yours or varying in small or large details. Some versions made different choices this morning. Some are living in worlds where history unfolded differently. Infinity ensures repetition. It's not a question of if, but of how many, and the answer is infinite. The revelation is disorienting. If there are infinite copies, what makes you unique? What distinguishes this version of you from all the others? The answer is location. You are here, experiencing this moment, in this universe, in this galaxy, on this planet. The other versions are elsewhere, beyond the horizon, forever inaccessible. They exist, mathematically, but they're not part of your observable universe. They can't affect you. You can't communicate with them. For all practical purposes, they might as well not exist. But the possibility remains, a strange consequence of infinity that pushes at the edges of identity and meaning. Infinity also means the universe has no center. In a finite cosmos, you could imagine a central point, a place from which everything radiates. But infinity has no center. Every point is equally valid, equally surrounded by infinite space in all directions. Earth is not at the center. The Milky Way is not at the center. There is no center. Every observer, everywhere, sees the same basic structure, the same cosmic web stretching in all directions, the same horizon defining their observable universe. Infinity democratizes location. No place is special. Every place is. The revelation also changes how we think about the Big Bang. If the universe is infinite now, it was infinite then. The Big Bang didn't occur at a single point. It occurred everywhere, throughout all of infinite space. Every region was compressed, hot and dense, and every region expanded. The observable universe, our bubble, is just one patch that happened to be within sight. Beyond it, infinite other patches exist, all part of the same event, all expanding from the same beginning. The Big Bang wasn't an explosion in space. It was an explosion of space itself. Infinite space, all at once. But infinity also raises questions we can't answer. Is the universe truly infinite, or just so large that it seems infinite? Measurements can't distinguish between a universe that's infinite and one that's merely much larger than what we can see. If the universe has a slight curvature too small to detect, it could be finite but unbounded, wrapping around itself in ways that make it seem infinite from within. We might never know for sure, because the evidence lies beyond the observable horizon, in regions whose light will never reach us. There's also the question of what infinite means for the multiverse. If the universe is infinite, it might contain regions with different properties, different vacuum states, different physical constants. These wouldn't be separate universes, but different domains within the same infinite space. Travel far enough, if it were possible, and you might find regions where the laws of physics differ. Inflation theory suggests this is plausible, that the early universe's rapid expansion could have created pockets with varying conditions. But again, we can't test this. The regions are too far, beyond the horizon, inaccessible to observation. The revelation of possible infinity is humbling in a different way than size alone. Size, even 93 billion light-years, is still a number. It's large, but it's countable, comprehensible in principle. Infinity is not. It's uncountable, endless, a concept that breaks the usual frameworks. You can't hold infinity in your mind. You can only acknowledge it, nod toward it, accept that it might be real even though you'll never experience it directly. Some find infinity comforting. It means there's always more, always farther, always beyond. It means the universe doesn't end. There's no edge, no wall, no place where things stop. Infinity is generous in its endlessness. Others find it unsettling. If everything repeats infinitely, does anything matter? If there are infinite versions of you, what makes this life special? These are philosophical questions, not scientific ones, but they arise naturally from the revelation. Infinity doesn't just describe the universe's size. It challenges how we think about existence, identity, and meaning. But whether the universe is infinite or merely very large, the observable part remains the same. 93 billion light-years across, filled with galaxies, structured by the cosmic web, expanding outward. That's what we can see, and that's what we can study. The infinity beyond, if it exists, is a possibility, a mathematical consequence, a revelation that shifts perspective without changing the immediate reality. We live in a bubble, and whether that bubble is part of something infinite or just very large, it's still vast enough to hold more than we'll ever explore. The revelation, then, is not about certainty. It's about possibility. The universe might be infinite. It might not. The data hints, but doesn't confirm. And in that ambiguity, there's room for wonder, for imagination, for the humbling awareness that, even after measuring so much, we still don't know everything. The universe keeps its secrets, reveals them slowly, and leaves us with questions that might never have answers. And perhaps that's fitting. Infinity, if it's real, is not something to solve. It's something to contemplate, to sit with, to let stretch the mind until the boundaries of thought dissolve and all that's left is awe. After the numbers, after the measurements, after the theories and debates and revelations, there comes a quieter moment, a time to step back from the data and simply reflect. The universe is 93 billion light years across, possibly infinite beyond that. It contains 2 trillion galaxies, each with billions of stars. It's been expanding for nearly 14 billion years and will continue expanding forever. These facts are true. But what do they mean? Not scientifically, not cosmologically, but personally. What does it mean for you, lying here now, to exist inside something so vast? The reflection begins with acceptance. The universe is large. You are small. These are not judgments. They're simply descriptions, measurements of scale. The vastness doesn't diminish you. It contextualizes you. You're not the center, not the purpose, not the reason the cosmos exists, but you're part of it. Every atom in your body, every breath you take, every thought that passes through your mind, all of it is made of the same substance that makes stars, galaxies, and the space between them. You're not separate from the vastness. You're an expression of it. There's peace in that realization. For so long, humanity struggled to find meaning by being central, by being special, by believing the universe revolved around us. But centrality is a burden. It demands that everything have a purpose tied to us, that the cosmos justify our existence. Letting go of that burden is freeing. The universe doesn't owe us meaning. We create meaning here, in this small corner, for ourselves. And that's enough. The vastness also offers perspective on suffering. When life feels overwhelming, when problems press in, when the weight of the day becomes too much, it can help to remember the scale. The universe is 93 billion light years across. It's been unfolding for nearly 14 billion years. It will continue for trillions more. Your troubles, real as they are also temporary, small against that backdrop. This isn't to minimize pain or dismiss difficulty. It's to remind you that hard things pass. The universe continues. You're held by something larger than your problems, carried forward by the same flow that carries galaxies. There's also peace in the realization that you're brief. Your life, measured against cosmic time, is almost nothing, a flash, a blink. But that brevity is what makes moments precious. If you lived forever, nothing would feel urgent. But you don't. Your time is limited, and that limitation gives weight to how you spend it. The vastness of the universe doesn't make your brief life insignificant. It makes it rare. Out of all the eons of cosmic history, this tiny slice is yours. That's extraordinary. The reflection also includes gratitude. You exist during a time when the universe is visible. The stars are still bright. The galaxies are still within reach of observation. The cosmic microwave background still glows faintly from the early universe. In the far future, none of this will be true. The expansion will carry most galaxies beyond the horizon. The stars will burn out. The sky will darken. Future civilizations, if they exist, will live in a lonelier universe, one where the evidence of cosmic history has faded. But you're here now, in the golden age of cosmology, when the universe reveals itself generously. It's structured. Galaxies cluster into filaments. Stars follow predictable cycles. Light travels at a constant speed. The laws of physics hold everywhere, from the smallest atom to the largest galaxy. This order, this consistency is comforting. It means the universe is knowable, at least in part. It means the questions we ask can have answers. It means there's a logic underlying the vastness, even if we don't understand all of it yet. The reflection also acknowledges mystery. For all we've learned, there's so much we don't know. What is dark matter? What is dark energy? Is the universe infinite? Are there other universes? What happened before the Big Bang? These questions remain open, and they might stay open for generations. But the mystery isn't frustrating. It's inviting. It means there's always more to discover, more to wonder about, more to explore. The universe doesn't reveal everything at once. It unfolds slowly, patiently, and there's peace in knowing that the journey of understanding is ongoing, that we're part of something larger than ourselves. Finding peace in vastness also means accepting that you won't. You'll see most of it. You'll never visit another galaxy. You'll never travel to the edge of the observable universe. You'll never see the other side of the cosmic horizon. And that's okay. The universe isn't meant to be conquered or fully explored. It's meant to be appreciated, wondered at, contemplated. You don't need to go everywhere to find meaning. You just need to be here, aware, present, alive to the fact that you're part of something immense. There's also peace in the smallness. Yes, you're tiny compared to the cosmos, but small doesn't mean powerless. You have thoughts, feelings, relationships, choices. You can create, love, learn, grow. The universe might not notice you, but you notice it. You can look up and see the stars, read about galaxies, feel awe at the scale. That awareness, that consciousness, is itself extraordinary. Out of all the matter in the universe, most of it is inert, unconscious, unaware. But you're not. You're a part of the universe that can think about the universe. That's rare. That's valuable. The reflection brings you back to where you started. A room, a night, a body resting. The journey through cosmic scale has been long, stretching across billions of light years and billions of years. But it ends here, with you, breathing, thinking, present. The universe is vast. You are small. And somehow, both of those things are beautiful. The vastness doesn't erase you. It frames you. It gives context to your life, perspective to your choices, depth to your existence. Finding peace in vastness is not about ignoring the hard things. It's not about pretending life is easy or that problems don't matter. It's about holding both truths at once. Life is hard and the universe is vast. Problems are real and they're also temporary. You're small and you're also aware. The peace comes from accepting the paradoxes, from letting the scale sit alongside the personal without requiring one to dominate the other. So as you rest tonight, let the vastness hold you, not as a weight, but as a presence, something that surrounds you, contains you, carries you forward. You're inside the universe, part of its unfolding, a brief spark in a cosmos that burns with trillions of lights. That's enough, more than enough. It's everything. And in this quiet moment, as the numbers fade and the measurements settle into something softer, you can find peace. Not because the universe is small, but because you're part of it, held by it, connected to it in ways that go deeper than distance, older than time, and more real than anything you can measure. You've travelled far tonight, from the familiar space of the room around you, to the solar system stretching light hours across, to the Milky Way spanning 100,000 light years, to clusters and superclusters and the cosmic web threading across billions. You've reached the edge of the observable universe, 93 billion light-years in all directions, and glimpsed the possibility that space might continue forever beyond that. The journey has been long, the numbers large, the distances almost incomprehensible. But now, gently, it's time to return. Time to come back to where you are. To this moment, to the quiet stillness of now. The universe is vast. That's been the thread running through everything we've explored tonight. 93 billion light-years across, possibly infinite, filled with 2 trillion galaxies and more stars than we'll ever count. The scale stretches beyond imagination, beyond what the mind was built to hold. And yet, for all that immensity, for all those light-years and galaxies and eons of time, you are here, right here, in this moment, in this body, on this small planet, orbiting an ordinary star in one small galaxy among billions. That location, that here, is not insignificant. It's where your life is happening, where your thoughts occur, where your breath rises and falls, where love and wonder and curiosity exist. The universe might not revolve around, to you, but your experience revolves around this point in space and time. This is your here, and that makes it special, not because the cosmos selected it, but because you're experiencing it. You are here. That's the final truth, the closing note that brings the journey home. After all the measurements and theories, after all the expansions of scale, you remain here. The vastness hasn't carried you away. The numbers haven't dissolved you. You're still present, still breathing, still aware. And that presence, that simple fact of being here, is enough. It's always been enough. The journey outward was to show you the context, to give you the frame, but the picture itself, the thing that matters, is you being here, now. There's no need to hold on to everything you've heard tonight. The numbers will fade, the scales will blur, the details will soften into something dreamlike. And that's okay. You don't need to remember every distance, every galaxy, every measurement. What matters is the feeling, the sense of scale, the quiet awareness that you're part of something vast. That awareness will stay with you, not as facts to recite, but as a shift in perspective, a gentle reminder that the universe is large and you're small, and both of those things are fine. As you settle now, let go of the need to understand it all. The universe is too big for that. Too complex, too layered, too full of mysteries that haven't been solved. You don't need to grasp everything. You just need to be here, resting, breathing, letting the vastness exist alongside your smallness without conflict. The cosmos holds you whether you think about it or not. It carried you here, across billions of years of cosmic evolution, through the formation of galaxies and stars, through the cooling of a planet and the emergence of life. You're the result of all that history, a brief expression of the universe's unfolding. And now, tonight, you're resting. The stars are still burning. The galaxies are still, drifting apart. Space is still expanding. But you, here, are still. And that stillness is as much a part of the universe as the motion. The cosmos includes both the vast and the intimate, the ancient and the momentary, the immense and the small. You don't have to choose between them. You embody both. The closing is not an ending. The universe doesn't end. It continues, expanding, evolving, unfolding in ways we're only beginning to understand. But your journey through tonight's exploration is complete. You've seen the size, felt the scale, touched the edges of what we know and what we wonder about, and now you can rest, knowing that the universe is still out there, still vast, still beautiful, and that you're part of it, right here, right now. You are here, on a planet that's spinning and orbiting and moving through space, inside a galaxy that's rotating through the cosmic web, inside a universe that stretches beyond sight and possibly beyond measure. But for now, none of that motion matters. What matters is this stillness, this breath, this moment of rest. The universe has given you this pause, this quiet space between the vastness and the everyday, and in this space you can simply be. The stars you've never seen are still shining. The galaxies you'll never visit are still spinning. The space beyond the horizon is still stretching, but here, in your small corner, in your brief moment, you're enough. You don't need to be more. You don't need to span light years or contain galaxies. You just need to be here, breathing, resting, present. That's all the universe asks. That's all you need to offer. So let the numbers go. Let the distances fade. Let the immensity settle into something soft, something that feels less like facts and more like a lullaby. The universe is large, yes, but it's also gentle. It holds you the way it holds everything, not with force but with presence, not with demands but with space. And in that space, you can rest. You can close your eyes, knowing that the cosmos continues around you, vast and quiet and patient. You are here. The universe is there. And the gap between here and there, between you and the vastness, is not a separation. It's a connection. You're not apart from the universe. You're part of it, made of it, held by it. And tonight, as you drift into sleep, you can carry that with you, not as weight, but as peace, not as burden, but as belonging. The universe is 93 billion light years across, possibly infinite, filled with wonders beyond counting. But it's also here, in this room, in this breath, in this quiet moment of rest. Both are true, both are real, and both, together, are enough. Welcome home. Welcome to here. Welcome to the quiet center of everything, where the vastness and the stillness meet, where the cosmos and the self touch, where you are exactly where you need to be. You are here. And that is enough.